Okay, thank you very much. Good morning. Yes, my name is Chris Marone. Happy to be here. Really enjoyed this workshop, and I wanted to especially thank Anthony Sladen for, not only all the work about putting it together, but then taking care of us all week long so we don't get lost or hurt or anything else. So, okay. Yes, I want to talk about 2 or 3 different things, and I like to follow the style of making this a school. So the beginning of this will be maybe too simple for lots of you, but hopefully accessible to everyone at some level. I have 2 or 3 things that I want to say. I didn't change my title. I like someone the other day, they changed their title completely. I didn't do it. I added to my title because I want to show you a few things at the end about how we're using machine learning to learn some more about laboratory earthquakes and also about earthquake physics in nature. So I say learning from laboratory earthquakes, and that'll be a theme of the whole first half of my talk about what do we know and what do we think we understand about how laboratory earthquakes work and how that applies to tectonic earthquakes. I'm not going to go through this in super great detail right now, but I'm going to come back to it, and since you're looking at it, I want you to see a few things. This is the shear load point displacement in an experiment. This is the shear stress. And so this is a repetitive sequence of in this case, 3 laboratory earthquakes where there's a cycle of building up stress, and then the stress drops. And what you see here are measurements of the elastic properties of the fault zone. Okay? There are two simple measurements. One is the wave speed through the fault zone, and then the other is the amplitude of the transmitted wave. Okay, so 2 simple things about the elastic properties of the laboratory fault zone. This is a laboratory fault zone. It is broken, there's shear localization within it. There are many aspects of this that are similar to what happens in tectonic faults. And what I want you to see is that the shear wave speed, the velocity drops when there's a laboratory earthquake, and the transmitted amplitude drops. And this isn't hard to think about because all of the contacts that have been there that have strengthened during the seismic cycle, in the early part of the seismic cycle when the fault was more or less locked, they are getting stronger and stronger, their stiffness is getting bigger, and so the wave speed goes up and the transmitted amplitude goes up. And what's interesting and important to see is that there's a systematic relationship between the shear stress and the velocity and the transmitted amplitude. It makes sense in different ways, but it also just provides an obvious precursor. You can clearly see that the velocity is changing before the event happens. And that is one of the things that makes it possible to apply machine learning techniques to predict various things about that. So that will go along as I go. There are many people who've been, over the years, trying to help me learn things. I'm a slow learner, so lots of people have to help me learn things. And I list lots of people's names who've helped me, including, and then starting with people who are going to talk in the next couple of days. Fabio Corbi is here, Giuseppe Volpe, right after me, or maybe right after Michele De Solda, and Michele Mauro is also here. So lots of people have been involved in this. You'll meet them along the way. I want to show you some aspects of different kinds of laboratory experiments. I'm going to draw a few examples from big data sets associated with laboratory shear experiments. And I'm going to take them from different cases. This is a buried granite, it's not westerly granite, sample that's at Penn State University, series of strain gauges along a fault. This is a single direct shear configuration. There's a hypothetically frictionless bearing on one side of it. And you can shear this thing. You're measuring with a displacement transducer to see exactly what happens with it. That's the scale of it. This is common in our experiments. It's what we used in the last data set I just showed you. You can call them laboratory seismometers. You can call them what you want. They're piezoelectric crystals. They're transducers that turn elastic waves into electrical signals, and vice versa, right? You pulse this thing and it generates an elastic wave, and then you listen on the other side. This is a new machine we've built in Rome in the last few years, and we've started to work with. It is almost a meter long, and I want to show you some results from what happens with eddy current sensors that measure the spatial temporal variation of slip along the surfaces. Okay, so these are all experiments, simple experiments in direct shear, either double or single direct shear. Another configuration that I'll draw a few things from looks like this. This sits inside of a pressure vessel. It sits inside of a loading frame. And it is a configuration where you can take a couple pieces of, this is westerly granite. You can see the way these surfaces fit together. And in fact, in this particular case, we broke the surfaces after cutting them into this configuration that fits into these loading platens. These loading platens have a bunch of PZTs in them, so we can interrogate the elastic properties. And they have the capability of flowing fluid down parallel to the shear direction in the fault, so we can implement fluids and also keep track of what happens with the roll of fluids. Okay, so just to highlight a few other things, there's another machine that's been built recently in Rome, and really entirely by Marco Scaretti and Cristiano Calatini, and it's called Brava 2. It's another machine like this. It's a biaxial loading configuration with a pressure vessel that allows you, in that case, to do essentially true triaxial loading, because you're controlling this load, and the confining pressure around in a jacket that looks like this when it's actually inside. There's a flexible latex jacket that goes around this or other types of configurations. Okay, and now, again, so that making sure people who haven't seen laboratory experiments or who don't normally think about laboratory experiments can think about, let's say, exactly what we're talking about. Super simplistic schematic made many years ago by a student named Matt Knuth. But this is showing you double direct shear, right? So we're applying a stress normal to the fault plane, and then we're shearing it. And we build the samples so that these are identical. In most cases, that's possible. In some cases, it's not. It's really impossible to make them identical, but normally they're basically identical. And then, like I showed you in Rome, but also this is the Penn State configuration, this pressure vessel can be put inside this, and then with a jacket, you can apply fluids and interrogate what happens under a range of conditions, okay? And so the stresses are not huge here. The stresses for this are almost 100 MPa, but let's say only that. Okay, now I want to stress, I'll tell you 2 or 3 things that are going to be important. I'll come back to many times. One is the value of having repetitive events in an experiment. So repetitive stick-slip events. So I'll just use the terms stick and slip sliding, and laboratory earthquakes the same in this particular case. But what's been useful recently, and I think in the last 10 or 15 years especially, is to be able to run experiments where there's hundreds of laboratory earthquakes. And not just simple repetitive events, periodic events, but events where there's real complexity in the nature of the interseismic time, if you want, or the stress drop or other things. So 2 things that are super important, and you can see here, is that there are many events. So this is the configuration. Hopefully you've already seen this long enough to realize, okay, this is the control, so-called load point displacement. It is the shear displacement on the fault on either side, here measured in millimeters. This is the shear stress that's being measured along these faults. And what you can see here is that we start out, we load up, nothing really happens. It's just sliding along stably. It's hardening. It's useful to cycle the load, the shear load. This generates a mature fabric, generates the fabric more quickly. And I'll talk about the variations in that fabric and behavior as a function of shear displacement. Or we could talk about shear strain within the fault zone. And what I want you to see here is that initially it's just sliding along stably, kind of nothing's happening. There's lots of interesting things you could do in that configuration. But in this particular experiment, we took advantage of something that we learned how to do, and that is make the sample transition from stable to unstable behavior. So on its own, there is a transition to these instabilities. At some level, this looks like noise. It's not noise. When you zoom in, you see that there are lots of events, and they're not periodic in this particular case on purpose. We wanted to try to produce complicated events, and that's one of the things I'll come back to several times. And then when you zoom in further, you see that. And then down here, I'm showing you the kind of data that was used to produce that first plot in my title page, right? That was showing you the velocity and the transmitted amplitude, and these are the individual elastic signals that we shoot through the fault zone. It's easy to set these things up so that you can measure the elastic properties every millisecond. You could measure them even more. So we're sending waves through. They take only a about 10 microseconds to go through the sample. And then by doing careful cross-correlation, you can see tiny variations in the velocity and the transmitted amplitude in this configuration, okay? So I'm showing you an experiment. I'm going to come back to some things about it. But the fundamental thing I want you to think about here is that having lots of these is really important to understand, in the end, to have an understanding of what's happening, okay? Controlled conditions, systematic behavior, okay. And it already occurs to me to stop just long enough to say, if you want a question along the way, don't wait. Just interrupt me. It'll be better for me. Tell me.
Those time series, like say shear stress, like when the sample is going down, like which part is it measured at? Does that make sense?
Yeah.
And like when you have time series, at what point along there is it measured?
Well, so we're measuring continuously, and maybe it's even better if I go back one more. We're measuring continuously, and there's lots of different transducers, but one of them is this displacement transducer that is measuring the base of the machine relative to the top of the sample. So we're measuring the slip across this surface, and we're measuring it continuously at 10 kilohertz, and then saving it, okay, it depends, but yeah. So the displacement measurement is between these two surfaces, the shear displacement on the fault.
But which point along there is it? Like which point in space, I guess?
So if I go back to the image to, sorry, I don't have my mouse here yet. Where is it? Okay, just go like this.
Oh, is it? Yeah, I guess, are you thinking of the whole block moving together? Oh, okay.
Right here, the whole block is moving in a sense rigidly.
Okay.
So I'm measuring the stress at the top, and I'm showing you the displacement across it. I'm going to show you also what happens to spatial temporal variations, and Giuseppe is particularly going to focus on that idea that we can see slip pulses moving along here at different time scales. Okay, this is just a function of displacement. Something else? Yeah?
Sorry, I just don't get why the shear stress transferred from the stable to the unstable.
Yeah, very, very good, because it's exactly one of the points I want to come to. Why do we have stable sliding here and unstable sliding there? I'm not going to try to answer right now because I have 5 or 6 slides that address that exact point. Tell me on. What else?
Why is the double shearing?
I'm sorry?
Why the double shearing?
The double shearing allows, this was kind of invented first in the engineering literature and then championed by Jim Dietrich. Because he realized that if you want to apply a big force here and you want to keep it constant, then it's easier to have both of the surfaces that are moving be the ones that you're studying. So you can turn this surface into a frictionless bearing, right? So there's plenty of them. We use them too, so-called single direct shear configurations. We saw a couple of them the other day. But in most cases, we don't know enough about the frictional properties of this surface to just ignore it. Like we can build a surface that has very low friction, but then we want the friction, then we want to also understand the memory effects of it and the velocity dependence of it. So it can be easier to just apply a load on 2 surfaces, and then the only thing that's moving are both the things you're interested in. Something else? Okay, so yeah, please feel free to stop me along the way. All right, I already said a few things about this. Maybe I'm just going to kind of skip over this. I want to the idea that we're going to be able to understand something about precursors by measuring these things and continuously measuring the elastic properties during shear. So we're measuring we're measuring everything, but here I'm just showing you the shear stress and the shear displacement, and we're measuring it typically 10 kilohertz and then averaging down to some reasonable rate to record things. I'm not going to go into too many details here. Beyond this, that if we want to generate models that we really have an understanding of, and especially if we want to generate so-called explainable machine learning models, then it's really useful to work with a system that we already know a lot about. A system like this, where the systematics of the relationship between the peak slip velocity, so these are data points from hundreds of laboratory earthquakes, like I've shown you before. I'm showing you the peak shear velocity that occurs during that slip event, which we measured directly with the LVDT or DCDT. So we have a displacement measurement, and then of course we know the velocity. And here I'm just normalize that velocity by the shearing velocity. We're typically just shearing at a few microns per second, but could be faster. I'll show you some of that in a minute. And then this is the stress drop. This is the cumulative co-seismic energy, just listening to the fault. So listening to the micro-earthquakes, the acoustic emissions that are occurring in the fault zone, and then keeping track of the energy that occurs in one seismic cycle. There are a few things about this that are easily understood after you've looked at this for a while. If you're looking at it for the first time, well, I don't know, maybe you do easily understand it. I'm not sure that I would, but I can tell you that this relationship between peak slip velocity and stress drop is exactly what you would expect from an unstable system. The bigger the stress drop is, the more energetic the event is, and the faster it slides. And then what you also see here is that for bigger stress drop events, there's a lot more acoustic energy that is released during the seismic cycle, okay? So I'm showing you this for one reason, and that is to again, emphasize the idea of running experiments where you have lots of events, and that helps us understand them, and it also helps us understand how to put it into that context. Okay, now I want to come to this good question that was asked before about how do we get from here to there? So I'm showing you a series of measurements. This was part of Marco Scudery's PhD thesis. I want you to see that at this normal stress, the system is just sliding stably. There's nothing interesting about it, but it follows Coulomb's behavior. So I'm showing you the coefficient of friction, always at this scale, so pretty zoomed in, and I just offset them here. So there's nothing interesting about the fact that this one's higher than this. Just offset them on this plot so we can see all of them together. They're all plotted at the same scale. This is time, that's 20 seconds. At 13 megapascals, we just see stable sliding. At 13.5, we also just see stable sliding. And then as you go up, you see different kinds of behaviors. At 25 megapascals of normal stress in this system, there are repetitive, simple laboratory earthquakes. And as we go down in normal stress, the stress drop changes. That's what that was in the last plot. And then we find a regime in here where things are pretty complicated. And this is interesting. So I said in the title of my talk, and I said here again, I want to talk about the full spectrum of slip modes, and this is what I mean by them, right? We could talk about the spectrum of slip modes in tectonic faults. I think there's perfect parallels, but here I'm only talking about the lab data. I'm talking about fast laboratory earthquakes with a last dynamic rupture. These events have audible coupling. They're over in a few milliseconds, and the slip rates are fast. And then there's no events here, and these events in here are slow. And so there's a bunch of things that I'm going to go through a little bit, both to talk about the transition from stable to unstable and to highlight a few specific things. And I'll just start with that one right there. This plot was already shown a few days ago. This is a plot from Bertrand Roux-de-Duc's work. And I'm sorry I don't have it here, but it comes up in just a second. This is laboratory data that was collected in my lab. In this 2017 paper, I was not directly involved in it. It is a measurement of the acoustic transmissivity and acoustic signal converted to strain. And what's interesting is this, which I highlighted over here. In a way, these are tremor-like events, tremor-like in the sense that you don't see an obvious P or S, tremor-like in the sense that it's rich in a particular frequency band, but not everything. And then, as you get closer and closer to failure, you see things that are more like a normal earthquake, with a distinct P arrival and S arrival, and fast. And it's the complexity of these events, too, that help us understand something about how these things work. So I'm going to come to that in a couple different ways. I also want to focus on this at some point, a little bit later, and Giuseppe Volpe is going to tell you a lot more about this general idea, not using this configuration, but this idea that there's partial rupture in many cases. Okay, I don't have that image up here again right now, but someone asked about where are we measuring slip, where are we measuring load. And this is, here we are measuring the displacement along the fault surface at many different places. And what you see is that when you have one of these kinds of events that's only a small slip, there's a differential amount of slip that occurs in different places along the fault. So I'll come back and I'll show you more about that. But generally what you can see already here is that this end of the fault is just sitting there doing kind of nothing. This end of the fault is creeping a little bit. And so when it slips, it slips as a pulse and doesn't produce the major stress drop that you get over here. Okay, so there's partial rupture in some cases along the surfaces. And those data are just taken from something like this. Okay, so blue is that end, and yellow is this end. And then we're looking at the variation along the surface of this fault. It's 70 centimeters long, it's almost 80. And we're looking at how differences in the slip, the spatial distribution of slip, couple into the way stress drops. So I'm simply here showing you a range of things that can happen. And then I want to talk about the physics of why it happens. So we have partial ruptures, that we already showed you. And there's also examples of things that are confined ruptures. You basically don't see much at all. This is the macroscopic average shear stress on the fault surface. Right? So this is measured with a load cell that's measuring how much force it takes to push that block relative to this. And this is a single direct shear configuration where, like everyone else, we produce another slip surface up here on the top that allows this block to move relative to this one. And either with Teflon or Molykote or some kind of lubricant. And you can see that this end of the fault is slipping, this one is not. And there's a little hiccup in the stress strain curve, but nothing interesting, nothing super major about it. Okay. So now, coming back to this, let's be a little bit more specific about this transition from stable to unstable behavior. This is an experiment like I showed you before. It's not the same one. It's in this double direct shear configuration. It's with a sample that's about 10 centimeter by 10 centimeter, the nominal contact area. And it's with a granular quartz material, a powder that simulates a real fault zone. And there's this spontaneous transition from stable to unstable behavior that you can see right here. And because we have local measurements, we can see the way slip accelerates, and we can, of course, then measure the local slip velocity on the surface as well. So if we want to think about why that occurs from my point of view, and especially from the point of view of this school, just go way back to the beginning of, well, it's not exactly the beginning, but it's one of the beginnings of connecting stick slip to earthquakes. This is a famous paper in 1966 by Brace and Byerly. This is the title. It was published in Science in August of 1966. And they talked about the transition between these two behaviors, right? In one case, it's just stable. In another case, there's stick and slip. And they said, well, why does it happen? How do we think about this? And what does it mean? And they had a few events. They had enough to pick out a story. They understood the physics of this system. And so let's look at the simplest way to think about this system. That system can be thought of as a so-called spring and slider. We're applying a load somewhere. There's an elastic interaction between that place where we apply the load and the frictional surface. So here, schematically, friction is green. And what they say, and which, I don't know, probably all of you have seen this in different ways, this is not at all surprising, that there's a stability transition that occurs as a function of that spring stiffness. So if you put this in a very stable, high stiffness system, it becomes stable. And you can see exactly why that's true if you admit that friction is at least this complicated. Right? So this is a so-called slip weakening friction law that could be attributed to many different places, and Palmer and Rice is a good one. But it just takes the idea that friction along this surface right here might, if it decreases at a rate like this and then becomes constant, there's a change in the frictional strength, and that change occurs over some slip distance. And this is a super important concept for lots of things that I'm talking about and that we think about for earthquake mechanics. This has units of stiffness. If I multiply this friction here by the normal stress, then I have a change in stress divided by a displacement. That displacement is the critical slip weakening distance. And this case of C then is exactly this. This is the way it should be thought about. It's the rate of frictional weakening with slip. It's a rate not with time, but with slip. How fast does friction reduce as a function of slip in this way? And I can tell you, this is super simplistic. It's useful. It's not right in different ways. My friend Sylvain Barbeau the other day told us a lot of interesting, more complicated things about friction. He didn't even bother with slip weakening because it's not super, different parts of it are wrong, but not completely wrong. And so when I to think about this transition question that was asked, if we want to think about this transition from stable to unstable behavior and even the complicated stuff in between, we can do that using this kind of law. We can define, it's useful, I'm going to show you several of these diagrams, and I don't know for you, but for me, I like to think of these as thermodynamic phase diagrams. Here we are, we just have a system with one variable, it is the stiffness, and there is a critical stiffness that defines the boundary between these two regimes. This one's stable, this one's unstable. Plotted as a function of nothing. I'm going to start adding some things to that plot. But it helps us understand how that transition occurs because normal stress is in this critical weakening rate. And you can already see, so if I just have one stiffness here and I load it at different normal stresses, the higher the normal stress goes, the more I'm in this regime here down at the bottom. So I'll say more things about that. We've known for a long time, so some of what I just showed you came from 1966 and around that time, even before. And then this idea came in 1984, and again, I'm sorry, I should have Gu et al. And Rice and Marina, 1983, 1984. It was about that time that people started using rate-state friction, and they understood that, well, we can add to this stability diagram, and now I don't want to just show it as a function of k. I want to show k over k sub c. So I've got this weakening rate, and I want to talk about the idea of I want to perturb the system with small changes in something, changes in velocity. I could perturb it with changes in normal stress. Any of the control variables could be thought of in that way. And what you can see is that at any given value of k over k sub c, if k is way bigger than k sub c, that is the stiffness of the loading system, the elastic surroundings are much stiffer than the weakening rate, then I'll get stable sliding for anything except for a really big perturbation. And then I could produce some unstable behavior. And then there's this interesting region in between that I can just call quasi-dynamic. It's not fully dynamic, it's not fully static, so it's useful to use that term quasi. Again, so thinking about that weakening rate, okay, so it's taking some steps and thinking about what happens here. And what you can see in this system there is that there are tiny little self-generated perturbations. We don't generate those perturbations. Okay, sometimes we do, but in this particular case, there are simply natural perturbations in the system that eventually grow into an instability. And they do so exactly in the context of this diagram. So I want to keep adding to it. So if there's some questions now. Okay, so I told you slip weakening is too simple. And in fact, radiant state is also too simple. So Van told us many things about what was too simplistic about it the other day. But it's got some aspects that match what we see in the lab and that help us understand it. And so here it is. It is a statement about the idea that the shear stress at sliding is a function of some state variable and velocity. It's only these two things in this particular case. It could be a function of other things, but in this particular case, the normal way you write down radiant state friction is that you have friction is a function of these variables. If I just divide the shear stress by the normal stress, I get the coefficient of friction, and I get something that looks like that. And I'm sure lots of people have already seen different parts of it. We need a way of thinking about how the state, which could represent, other people talked about the other day, it could represent the contact area, it could represent the porosity within a fault zone. It represents something about the physical state of the frictional system. And now, from the work that was done by lots of people in the early 80s, and this is the original papers in Dietrich in 79 and Marina in 1983 that introduced these ideas. I'll say more about the state evolution law in a minute. But what you can see by doing perturbation analyses is that we can also define a critical weakening rate, just like we did with slip weakening. We can't draw it so easily anymore, but we have a critical weakening rate. It is weakening rate in the sense that the B minus A parameter times the normal stress is just exactly the same conceptually and numerically as the change in friction that we have here, right? So we have a static and a kinetic value. We're going to have to get rid of the idea that the kinetic value is constant, but don't worry, we can. All right, so now we have another way of thinking about this that connects into a more modern, sophisticated friction law. And I just wrote a few things here. My guess is that there are two choices, either you already know so much about rate state friction, this is just boring, or you don't know anything about rate state friction and there's impossible that in one slide or 5 is going to help you. Okay, so the lecturer's dilemma I'm not too worried about. But I anticipate that you're all fast learners, so if you haven't seen this, you'll be able to catch up quickly. We have a rule that relates, if I know the velocity and the state at any given time, then I can know the friction. That's what this says. And then I have a way to think about how state changes as a function of some perturbation. And this perturbation here is expected to be in terms of velocity. There are 2 ways that you can think about this. In the literature, you will see many people still use the aging law and the slip law. I don't know, it makes no sense to me. We don't talk about force law. Well, we say, oh, force and displacement, that's a law. No, we call it Hooke's law. We don't talk about the relationship between mass and acceleration and force as a random thing. We call it Newton's law. So according to me, we should just go ahead and call these things the Dietrich law and the Riemann law. They were introduced at the same time in different ways, but Rowena was really influenced by the work of Ernest Rabinowitz that I'll talk about in a few minutes, and really thought that the only way you could evolve the state was by having some slip occur. And so you can see in this particular case, as the velocity goes to 0, if we don't have any velocity, if the surface is not moving, then the state doesn't evolve. Now, of course, that's just an end member. It doesn't have to be true in every case, but okay. So there's a pitch of saying, why don't we just call these things Dietrich and Riemann? They did all this incredibly important work that we're all still using. This is showing rate and state friction with velocity weakening. And now I want to go back to this. And now I want to talk about this idea that there's complex behavior that was in this paper by Gu et al. This is a little bit of a codicil. I don't know if you know a lot about this already. In fact, you don't get that complex behavior unless you use a little bit more sophisticated law than the one I just showed you. There's not enough in that law to produce this. You need something else. Okay, so this is I'm going to keep using this critical stiffness because I want to try to interpret many of the things we're seeing in terms of variations of this. And I'm going to get rid of this term. We don't need it for the nucleation part of this. If we want to study something fully dynamic, then we need a more complicated model anyway, like Luis Gabriel uses. Then we need a lot of more terms anyway. But if we just want to think about nucleation, like the transition from stable to unstable behavior, then we can do this. It's good enough, right? And so that's what I'm going to do. When I talk about the variations in this, from stable to unstable, I'm simply going to use this part of it, okay? This is what often happens, at least for a talk like this. I have all of our data. I remember our own data. I just pulled plots from our data, but I could pull plots from lots of different places. And I don't see Corentin right now, but I know he's out here somewhere. He gave a talk in the Monday seminar series the other day. He's about to give a talk tomorrow, I think it is. Corentin Zilde. Where is he? He's right there. Okay, so I'll simply put this in here to advertise his good work, and also to say that there are lots of labs that are producing the kind of data that I'm showing you. Okay, so it's easiest for me to show our own data, but lots of different labs are showing this transition in behaviors. This is a different configuration that they're using, but you can see the same kind of transition that I'm talking about from stable to unstable behavior and different kinds of unstable behavior. And this round two also talked about stuff like that the other day. All right, so now I want to keep going and say a little bit more about this transition from stable to unstable behavior. And showing you 3 experiments here at 3 different normal stresses for the same material. This is again a granular quartz. We've looked at this in lots of different systems. We just have a lot of data for that particular system. It's shown as a function of the bulk shear strain within the layer. The layer is just a few millimeters thick. And you see that at 25 MPa, that happens at an earlier shear strain than it does at 20 or at 15. And then you see some details here I don't need right now. But what I want you to think about is the idea that K sub C is changing as a function of strain in a systematic way that we can measure. I just show you this to help you think about the idea that, no matter what we start out with in the lab, after we shear it at reasonable stresses, lots of things break, and shear localization occurs within the layer. Right? So it's not simply a granular system that has a constant particle size distribution or something. We could do experiments like that, but the real world involves breaking things and causing localization. And that happens in our experiments too. And we've known this kind of thing for a long time. In fact, if I if I had been a little more organized, I would have gone and taken some of Mike Blanpede's PhD work that showed exactly this kind of transition. This is, these are measurements here of B minus A, so, and as a function of shear strength. And what we've known for a long time is that many materials start out velocity strengthening at very low strains and become velocity weakening. So there's more shown than just that. But that's one of the things that happens as a function of shear strength that's been known for a long time, let's say. Then we also know this, and we know this just for a few systems. Last night, Ake was buying me a beer. He only bought me a beer so that he could ask me questions about this plot, so I put it in here. But we've known this, at least for some systems for a while, that as a function of accumulated shear strain, this critical slip distance gets smaller and smaller in a way that's consistent with the ideas of comminution and shear localization. So I have two different things, and then Marco produced this interesting plot. So it's a little bit tricky to follow, but not really, let's say. So as a function of shear strain, I'm showing you K sub C, and that is these black dots here. So I've made measurements of B minus A and D sub C, and I'm showing you what happens with K sub C. What you see is the K sub C goes up as a function of shear strain. And you can see exactly why that is here, because D sub C is going down, and B minus A is becoming more positive. B minus A, not A minus B. Okay, so it's becoming more velocity weakening, and the D sub C is getting smaller. That makes K sub C get bigger. And in our lab systems, these are measurements of the stiffness of our lab systems. They go up too, but then they just plateau. And what you can see is that at 15 MPa, it takes a while for us to meet this condition that K is less than K sub C. Because this is K, this red line, and this is K sub C. And so at some point, we've satisfied the instability condition that's been told to us, which we've measured. And that happens at an earlier shear strain for higher normal stresses, exactly predicted by that simple idea. Right? It almost looks like slip weakening. Okay, so schematically, this is what's happening. That as a function of shear strain, I can show stiffness, and I can talk about the real stiffness of our system. That is, so the way we're loading this system. It goes up initially as a function of compaction and densification within the fault zone, and then it just stays constant, more or less. And then K sub C does this. And it's possible to talk about a negative stiffness if we think about K sub C, because if it's velocity strengthening initially, then this value is negative. And then, so you start out down here, and then you become more and more velocity weakening and smaller critical slip distance. And you produce this transition. Okay, so that happens. And now I'm on to, I've done a few things, not super organized, but I'm in this diagram, I'm still talking about different parts of this. We've talked a little bit about this. I want to talk a little bit more about this. And I want to talk about the slow events and slow precursors that occur. But what I'm just showing you, and I'm about to show you much more in detail, is that this diagram that we originally had isn't correct even for simple cases. If I have a given value of shear strain, certainly I'll cross over this boundary this way, because I'll produce a stiffer system, that the critical nucleation length will get bigger and bigger. But if I'm near the stability boundary, if I now think in terms of shear strain, that's what I've just been showing you, then I can see that I'm going to cross the stability boundary, the phase boundary, like this. As I go to higher shear strains, I'm going to become more unstable. All right, so I plotted this backwards, so I should have changed it, and I won't do it on the fly. As I go to higher shear strains, I go into the unstable regime, and as I go to lower shear strains, I start out in the stable regime. Okay? So we can already see that K sub C is a function of shear strain, and I'll talk more about that. But I'm also going to show you that K sub C is a function of velocity in a simplistic way. So we want to talk about both of those things and think about both of those things. And here I'm going to now focus on velocity for a few minutes in these experiments. And I'm just showing you a data set that indicates this. And I'll show you different parts of it to convince you. But in these experiments, we can control the sliding velocity easily. And what you see is that if you go at 30 microns per second, you get one type of behavior. These are small stick-slip events. And if you go to 110 microns per second, you still have a kind of a velocity weakening character. And there's some noise to this. But the events are either zero stress drop or very small. And then if you go at a slower rate, you get bigger and bigger events. So again, what I can see from this is that this critical weakening rate, B minus A over D sub C, could be more complicated, but at least that. This is what happens as a function of velocity. If I go faster, I go into the stable regime. If I go slower, I go into the unstable regime. And exactly where that transition is, I haven't talked about. I don't know in every case. But we know in a few cases from the laboratory that we can cross over that boundary in a very systematic way, in a way that John Lehman, as part of his PhD work, went really to great lengths to try to understand. Lots of different experiments, controlling all the other cross-partial derivatives that could matter. If you think of that, that's an obvious thing that happens in the lab, is that as a function of shear strain, lots of other things change too, right? So you don't have a simple partial derivative with everything else held constant. You have to work at that to do that, and he did. And what you can see is at 3 different normal stresses, you have a range of different behaviors. At 5 MPa, at a low normal stress, is basically always stable. I showed you that even at the beginning. At 7 MPa, you see a transition. As you go to faster velocities, it becomes more stable. And at 12 MPa, it's mostly unstable. So you can see that transition in a range of ways right here. These are data from John Lehman's paper. Because he showed as a function of normal stress, the way this transition occurs from stable to unstable behavior, and how to think about it in terms of the instability criteria. He showed also the timer is a little complicated here. It says I've been talking for 9 minutes. Maybe all right, so now I want to pull together a bunch of things because I want to make a little point here about slow earthquakes. A little point from our own experiments about slow earthquakes. And that is, we see this transition. We see slow earthquakes in our lab experiments. We see, when you look at the events that are in a catalog like this, you look at all of these events. These are fast, these are super slow, these become more complicated. When you measure the details of all those, you end up with something that looks like this. We know what K sub C is. We know where we are in terms of K over K sub C in the lab. The control variable is typically normal stress, but it's also shear strain and velocity, in the way that I've been telling you. And then this is the peak slip velocity of the events. Excuse me. None of these are super fast, but what you see is that as you go more and more into the regime where K is less than K sub C, you become more and more unstable, faster and faster events. These are audible stick slip events. And we always have good measurements of them. Okay? And there's other things about them. This is a plot like I showed you right at the beginning, except for it's the other way around. This is the stress drop as a function of the peak slip velocity from a range of experiments. And what you see is if there's a big stress drop event, then there's a lot of energy in the system and the fault slides very fast. And it slides very fast in a way that's entirely consistent with what we know about the way K sub C changes as a function of strain and velocity. And so, coming back to this plot that I've now shown you many times, just want to talk about the idea of, in the lab, what do we need to make slow earthquakes happen? Okay, so I just focused on the lab for a few minutes because we've heard a lot about slow earthquakes in the last couple of days. I'm sure we're going to hear more about them. But in the lab, in these experiments, what we know is that B minus A and D sub C changes as a function of sliding velocity and also strain. The rate of frictional weakening changes that way. Really what happens in these slow earthquakes in the lab is that they begin to accelerate and then they lose the necessary condition to be unstable. They start to strengthen. They don't have to transition from velocity weakening to velocity strengthening. You simply have to transition from velocity weakening to less velocity weakening, and that's what will happen. Right? Okay, because now I've said a few things, and I wanted to take a little break here. I put this slide in here to remind myself to, first of all, thank the rest of the speakers who've come before me, because I really enjoyed these talks. And also I thought it would help me slow down a second, see if there are more questions. Tell me. Yeah.
So what do people mean by when they say conditionally stable faults make slow events?
Yeah, good point. All right, I'm going to come to it exactly. So let me explain by way of showing a few slides. But the conditional stability.
You told me I should ask that question.
I am going to talk about it, but it's going to take me 2 slides. But I think it'll be easier to just keep it as a conversation. Something else? All right, so I've been telling you a bunch of things about experiments that are happening in this kind of system. We know a lot about it. It's simple, and I want to focus on this just for a couple minutes. We'll focus on the idea that there's this slip gradient, and then we'll come back to the idea of conditional stability, because it's not exactly in this. Show you what regular-stick slip happens. And then I want to show you another data set from this machine. It's very like what I've just been talking about, the idea of slow slip and the idea of the transition as a function of velocity of K sub C. And what you can see, okay, this is just a record section of some measurements from that experiment. This is the shear stress that's applied on the fault. This is the shear displacement on the fault. And because the system is servo controlled, even though it's almost a meter long, we can control the rate of loading. So we can drive it at 3 microns per second. And then Giuseppe Volpe changes it to 10 microns per second, to 30, and 100, and 300. And what I want you to see is that there are a lot of events, complicated events. You see some period doubling kind of things, small then big, small then big. And then eventually it becomes almost entirely stable. And it becomes velocity strengthening out here. So you can see that from 30 to 100 to 300, we're actually increasing the frictional strength as a function of slip, not decreasing it. Okay. So what I want to do, let's talk about the conditional stability idea here, because a necessary condition for instability here is that B minus A is a positive number. If B minus A is a negative number, then I can go back to that plot, I won't, but then K sub C is a negative number and K is never going to be less than that. It's just impossible to have an instability, especially a sustained repetitive instability. Okay, so there is a critical rate of weakening with slip, and whether we have a really unstable system or a stable system or something that's in between depends on this parameter. And so we can think of the conditional stability here as if we're changing B minus A and B sub C, we can put ourselves in a situation that was going to be stable or unstable. And that's kind of what's happening as a function of velocity, what I'm showing you. Right? As a function of velocity, we're changing that parameter enough so that we lose the capability of making it be unstable. Okay. According to me, I've talked for 50 minutes, and I was thinking I was going to talk for 53.
10 minutes left.
Oh, it's still 10, according to you. Okay, that's great. Yeah. All right, so now I want to pull some things together from other experiences you have, maybe, and try to make a point that's connected to, for me, something simple. And let's start here. Okay, so we heard from some things. Actually, the dates you showed are 1821. I don't know 1821. He did his work. He published his work in mechanics in 1785. And one of the things he did was he was interested in the time dependence of friction. He was interested, what do you do after you build this boat? How do you launch it? How do you get it off the frame that you built it on? And so he studied how friction changed as a function of time, and he produced this data set. This is his data set. You can find it in a book. I plotted it as a function of log time. He actually thought about it in terms of a power law. But main point I want you to see is something I hope is simple for you. Surfaces that sit around in contact for a long time become stronger and stronger. And fortunately, they don't become stronger as a function of linear in time, because otherwise, if the door closed and it got a little hard to open, then in an hour, we'd never open it. Right? So it's log time. Okay, it doesn't change too much. This is a pretty simple thing to interpret, and you can see it exactly in this slide that someone showed the other day. Maybe I think it was Yoshi. This is Dietrich and Kilborg. These are see-through experiments, and they're showing you the area of contact between two pieces of plastic. And they're showing you how it changes as a function of time. And I want you to realize that, yeah, that's exactly what Coulomb was telling you too. All right? And now, I shouldn't take time on this, but I think it's kind of fun. Rabinowitz. All right, so that's what I thought I should do. Okay, so I'll take 2 or 3 more minutes and finish. Rabinowitz did this super interesting work in the 50s, talking about how you could transition from static to kinetic friction. He invented the slip weakening law. We always talk about it as later, but he invented the slip weakening law in this paper. He also has this 56 paper where it's clear when you read this little summary that he knew everything about rate and state friction. He has this little historical summary of friction. And this is in the 1700s. This is where friction doesn't change as a function of anything. And then in the 1800s, people had the idea that, oh yeah, maybe there's static and dynamic, so as a function of velocity, friction instantly drops, but then it's independent of velocity. And then he said, oh, well, maybe it's a function of velocity. And then he says here, oh yeah, and now, in 1956, we understand that lots of things in friction work like this. At low velocity, they're what we would call velocity strengthening, and then they become velocity weakening. So they already knew a lot about this system. And you can understand that in terms of Hertzian contact mechanics in a way that Sylvain talked about already. You can understand it from that. And it connects really interesting. It is the backbone of rate and state friction, right? So there it is. And here's an example of one of the things that you could show measurements that show how friction is a function of loading velocity and also other more complicated things. And then before I finish, I want to ask you, so according to me, Coulomb's measurements of this time dependence of static friction are very much like this. They are a backbone of this. And I just want to ask you, which group are you in? Because according to me, we know a lot about what to expect here, and I've already shown you some measurements of it, but I want to see, because if we look at measurements of shear displacement as a function of shear stress as a function of shear displacement, and then we drive at different rates, which group are you in? How many people are in group 1? Doesn't matter.
How do you define stress drop?
This is the stress drop from there to there. So the size of the stress drop, the magnitude of the stress drop.
So no seismological stress drop or...
No, this is a laboratory stress drop, but it could be a seismological one. So it could be a seismological stress drop that I get out of, moment area relationships, Brune model, let's say. Anyone in group 2?
But it's a trick question. It's none of the above.
Yeah. Everything's a trick question. I'm just asking you what group you're in. As long as slip velocity is a function of stress out. Or in group 3, how many people? Some people in group 3? A lot of people are in group 0. There's only 3 choices here. Okay? Let's look. I don't know, because I've shown you some of this data, and I want to make at least one more point before I finish, and that is this. Okay, this is what happens. It's a function of slip velocity. This is part of this idea that I said to you that the critical stiffness is a function of velocity, because as you go faster and faster, you transition to the point where stress drop is 0. You just have stable sliding. And this is exactly predicted by, I can say Coulomb, it's exactly predicted by rate and state friction. Okay. It tells us this. It tells us that, this critical stiffness is a function of velocity that looks like this. We can see it here. We can see it in those measurements. And it falls out of rate and state friction in a way that's not too, it's easy to reproduce, okay? So these are numerical simulations with it. You have to add something to deal with the dynamics. So you just add in radiation damping. And this is numerical simulations with a couple values that you can see up here. And you can see, yeah, it reproduces almost exactly what you see. It doesn't reproduce all the details of it. Okay, so in the name of thinking about, for me, why can't I see my mouse? Okay, I'm going to go here and there. So in the name of encouraging discussion, I'm going to go simply to a summary. No, these are all backup slides. So somewhere I see grazie, and I'll just go there. Yeah. Okay, in fact, maybe I'll just do it like this. All right, so there is a little bit of a summary. I didn't tell you about machine learning stuff. I highlighted it in the summary because I knew I wasn't going to get too close to it. So I thought, okay, I'll just include it there. And there are a few things about, well, I certainly got to say this about the physics of lab earthquakes are consistent with this. There's a lot of things that we observe and that are not very hard to explain. I want to thank Anthony Sladen again. He's there. And the importance of repetitive events. Okay. And all right, I'll just stop right there and talk about more of a discussion. Thank you.
So you mentioned a couple of times that
I don't have that functional form here, but yeah, it's a good question. I don't think I have a data set that's going to be easy to find. We know that d sub c is a function of velocity from experiments that I didn't show you, at least for certain types of materials. And it's a function of log velocity. And then b minus a, it really depends on the material we're talking about. But for this granular quartz material, b minus a depends on velocity, not log of velocity, but almost linearly with velocity. So in order to produce the simulations I showed you just a minute or two ago, I have to make, go back to those at least, I have to make b minus a function of velocity going from a small degree of, oh, no, it doesn't. It is log of velocity because this is basically the log of velocity itself, but it goes from slightly velocity weakening here to slightly velocity strengthening there for one type of material.
So, you didn't really talk about like the material property change in these lab experiments, but I think on the first slide you showed the precursory velocity changes in these experiments too. So suppose like when your K is below Kc, like there's still some material changes, in the medium. So like when you have a precursory velocity change, actually the nucleation size can be much smaller. So it's not like a linear function anymore. So I just wonder, like, how do you think this can change the KCK, diagram thing, like when you have the material property changes?
But so what we know from the lab is that K sub c changes as a function of strain and as a function of velocity.
Right.
And we can see something about the functional form of it. And I don't think it's connected directly to the precursor story as much as it is the acceleration of slip and the transition from stable to unstable behavior.
So like when you have a small precursory velocity change, that actually changes your nucleation size a lot.
Yes.
In simulations. I'm not sure if this lab experiment is the same, but I think it's changing the KC criteria.
Yeah, for sure. Oh, it's also changing the, what's happening in these experiments too, or you can visualize here is exactly what happens in your models, and that is there's a change in the elastic modulus, the shear modulus, all the elastic modulus, the material that's happening as a function of the seismic cycle. And so that would have implications for the critical slip distance. In a lot of these smaller experiments, we don't have the capability of like visualizing the spatial temporal variation of slip to really visualize slip pulses. But in the bigger experiments we do. So what we need to do is to put those things together. We haven't done that yet.
I have a question with your new machine or with the larger one. I mean, the stress part is even with the constant, within the band with a constant loading rate, same loading rate. What causes such variations in your larger experiments?
But so in those experiments, if you just go at a constant velocity, you kind of end up seeing one characteristic set of events, depending upon the normal stress. And as you accumulate strain, you see some variations in it. But especially in those, the wear rate is so low that you don't have a strong change in K sub c as a function of strain. But we are imposing velocity changes to try to understand what happened then. So I think maybe the answer is that, yeah, we're just imposing them.
When you report experiments that have all been done in one material or a couple of materials that you understand really well, to which extent do you think that's applicable to, what makes these materials behave this way anyway? If you were to redo these experiments with, let's say, steel or copper, or would you see, what is universal about this and what is less universal about this?
Yeah, it's a good point. And I had a slide that I skipped, and maybe I'll try to find it, but for some reason everything's incredibly slow. And that is a slide that looks like this. So it's easy to focus on. I've focused almost entirely today on some things about quartz powder and granular quartz. But lots of what I'm showing you also applies to these systems. I don't know if it applies. We haven't done much with clay-rich rocks. But we're looking at rocks that have, huge range in particle sizes and super highly localized shear zones. So I think some parts of this are generalizable, but no, it depends on, you say, does it apply to copper? Well, I know time-dependent aging applies to copper, and I know static and dynamic friction ideas from Rabinowitz's do. But whether or not I would see a velocity dependence of the aging rate in copper, I don't know. Yeah. No, it's a good point. And it didn't say enough about the fact that we're looking at simple systems, trying to understand what happens to those, and then, yeah, then it's a leap to decide if it really applies or how it applies to tectonic faults. I guess one thing I didn't say that I want to make sure I say out loud is that I'm showing you, and I've showed you at least in these simple systems that are granular. We have experiments with fluids. I didn't show you anything about them today. But you can produce slow slip without fluids, okay? I don't say that the beautiful dilatancy work that Nicholas showed us the other day, no, that could be exactly what happens on natural faults. I simply say that you don't need fluids to make slow slip. You can get slow slip to happen without fluids associated with this transition in case of C. And it might be one of the reasons why Romain showed that they have a paper that has exactly this title, and that is slow slip occurs everywhere. I think something like that is the title. It happens in many, many situations, not just on tectonic faults. It happens in landslides. It happens with glacial motion. So the mechanism that produces slow slip is probably more general than just fluid pressure.
I have a question. So you have seen that Kc depends on strain, on normal function, on velocity. So just one feeling I get in terms of numerical simulation with normal function, we understand it quite well. With strain, it seems to me that at one point it saturates, so maybe it's okay to say it's independent for major fault. What do you think about it? For my last question, I get the feeling with velocity we don't understand it so much, and we are not so much modeling it.
Yeah,
So
to impose velocity. Yeah, yeah. Well, I mean, you know very well that it's one of these systems where boundary conditions really do matter. So you can do experiments. In fact, Felice is doing experiments that are like that, where you've got a material that looks like it's steady state velocity strengthening, but when you subject that material to a constant shear stress that's near the failure stress, it starts to accelerate. So in that case, boundary conditions really do matter. And I think that's one of the points you're making. Maybe there was one I didn't catch, but whether in numerical simulations, you typically don't impose velocity, you impose some stress and watch what happens. So.
Maybe Michele can put the slide here, and we'll take one last question.
With the normal stress decreasing and the shear strain increase for the transition point from stable to the unstable.
Yeah.
Is it possible to build the physical mechanism for PC with shear strain and the physical process for shear strain?
Yeah, so there's several things in there. And a simple answer to your question is yes. Is it possible to build a model like that? Yes, it is. Because we have measurements of the relationship between the critical slip distance and the driving velocity. And we see that at least for certain systems, the critical slip distance goes up as a function of velocity, gets bigger. We also have experimental measurements where we can see variations in the critical slip distance. So let's picture we just do velocity stepping experiments to measure the rate of state properties. And we can see changes in d sub c as a function of shear strain. So we can see those two. And there are physical models for it, but probably that's something we can discuss after.
Thank you, Chris.
Oh, yeah, sorry. Yeah. Yeah, he advised me to put it on surrounding like that.
Can you hear me? Yeah, of course. Okay. May I start? Yes. So, good morning, everybody. I'm Michele De Solda, and I'm a first-year PhD student in Roma La Sapienza. And today I'm going to talk you about a struggle to try to apply typical seismic reflection techniques on laboratory experiments to see if it's possible to track fault structure evolution. First of all, I don't think I have to dig too much on it, but like faults are really complex structures, and there are people here around that have explained that the complexity of this structure can account enough for the changing on sleep behaviors, number one. Number two, we have observational data that say that this actually happens, like that fault fast sleep modify the geometry around and make slow sleep and the other way around. So one question that is like really a student question is maybe we can use the zone structure evolution to predict failure modes. So if I was precise on this point, some one of you should think this is weird, because if you know fault structure evolution, you already know. Like, how many of you think that trying this stuff is weird? And how many of you think that it's trivial? Okay. In some sense, that's already inside any rheological rate state law that you write, because of course you have the evolution of the friction, but you need somehow the evolution of the contact, and this is structure. And you need to know around your contacts what's happening in the sense of what's telling how the contacts are stay there and they don't move. So just read the guys. I'm not gonna dig really too much because I will get lost in rheology. One thing that Chris, thanks God, already explained is that well, the interplaying between the real stiffness around the fault, or at least around laboratory fault, and what we call critical stiffness rheologically, it's what can explain the critical change between stability and instability. So I'm a student, I'm not that smart on rheology, on obstruction, and the first thing I thought was, maybe this rheological stiffness is stiffness aware. So it's a real relationship between stress and strain in a point around the fault. So I went on and say, is there a way that I can see it? The answer is no. By the way, in the lab, we can try actually to do that because we can see the structure and the evolution of the structure. For instance, this is extremely localized zone on a synthetic gauge material after a while that you produce the fabric shearing. And so the main idea is like, well, I can see it sometimes. I can open the sample, check sometimes. I can try to check it continuously, constrain what's going on by sending waves through the sample. So this is seismic reflection in the lab. Theoretical framework, why this should work. Okay, this is like probably the basic of any course on mechanics, but I would like to remember to myself and to the other people that this was originally empirical. So while this is Newton's law, the fact that you move stuff because you compress it around, this is empirical. This comes from the lab. This one too, and they both works until on a normal sample you can put numbers between strain and stress. And this is local. So there's one point, this is really hard, to me it was really hard to grasp, is that I never see a bunch of stuff that move all together in a rock, because rocks is made of a lot of different stuff. So how is come out that I can use this equation on this scale to explain what's inside and what's happening inside? So how come up that actually this stuff produce waves when in a small scales we know that this can't happen. This equation break down. So we need a connection tool that is, whenever I can't write a density because, well, my rock inside is changing a lot, I need to do averages, and this is two-end member average. And I need to account for each phase that I can recognize. This is geology, so if I recognize principal zone, damage zone, this is two different phases. I should try to make average on it. And for each phases, I need somehow a law that explains how this phase changing, accounting, for instance, for porosity or for the volume that are comminuted. If you take the two the equation together, you have the wave equation. That's one really important point, is that this is local. So it's really hard to understand why, to me, it was really hard to understand why this equation can say something on this point when I'm looking between this point and this point. This is what you inject, you register in the other side. If this is not one number, what you look at the end of the registration does not look like the source. So this is a problem, but it's a tool, a sensitive tool. It means that if I throw an elastic wave inside a sample and I register it and they looks different, the waveform looks different, it happens something in the middle. And maybe I can try to reconstruct what was in the middle. So all the stuff that I'm talking about was just really to explain that in the lab, in a double direct shear experiment, and he has explained already it, again, thanks God, we just sandwich synthetic gouge inside the double direct shear experiment, and we produce shear fabric by imposing normal stress and imposing shear stress. So that's all. But we want to track the evolution of shear waves to the sample. So what we do, we go there and we get this piezoelectric sensor. We put it in one side of the sample and in the other side of the sample. We throw waves continuously, and we synchronize this measurement to mechanical data, so to stress and strain, to stress and displacement. At our scale, what we can say about how much we can resolve it. So this is the wavelength of our waves, more or less. We have piezoelectric that can produce at maximum 2 megahertz of frequency. You make the math. If we are lucky, we can see 0.25 millimeters in a fault zone that is around 10 times this. So we can at most make 10 points in the middle of this fault gauge. I was trying to say, okay, is it enough? They changing inside are sensitive enough that my velocity can tell me if the structures are changing. I didn't do properly the math so far because it's fresh result, but yeah, there should be a way, because while this comminute, so the principal stress comminute, there must be a point where even if the volume of this principal stress zone is small, this should go toward breaking, because we know that's at the point this break. And that's what I pretty much have done. That is seismic reflection. You open the book, Andreas Fichter, and you read how to move from the analytical wave equation to a finite difference scheme, injecting your source, and then find a way to measure how good was your synthetic waveform against the observed data in an interval to make this inversion possible, because I'm doing a solution that is really simple respect to what's going on in the sample, and then find a way to update this velocity model until this measure is good enough. There's a point in the middle that is not easy, but in the lab you have to make it. Like, how does it look, the source? Because of course you pulse electrically, but then you want to see the mechanical wave, and it's not that easy. That's again laboratory work. So we know that the solution of a wave equation, if the media is homogeneous, looks like the source. So we just put this piezoelectric sensor across a piece of iron and check how it looks the source, and we assume that how it looks the solution across an homogeneous media, and we say, well, that's the source time function. The reasoning for why we cut around the direct arrival, we just check around the direct arrival, is that, of course, the model is really simple. So I get mode conversion before and after, so mostly after. The geometrical splitting after a while will make the bouncing really not responding anymore with what is in nature because it's 3D. And then I want to avoid lateral reflection because like that's a confined sample, and so sooner or later the reflection from the boundary will enter in the weight. This is what I see, and I have override. I finish, okay. I can just show you that is, while you try to see this shear fault evolution, you can actually perceive that there are moments where the creation of the structures can be seen, imaged. And then that after a while, the typical procedure that we do of loading and unloading to make the structure being stable before making it unstable, it's actually what you should expect using wave equation as well as using cross correlation of travel time. So I leave here what's the idea at the end of my job, and I'm open for discussion.
Any questions in the room?
So acoustic transmissivity has been done across frictional interface since the 50s at least, and it's part of the classic books of Marone and Tabor.
Yeah.
And that's how we learn a lot about friction. So what are you trying to do beyond this? Are you trying to do tomography of the
Yes.
ground layer?
Yeah, I'm trying to do imaging because, of course, I'm starting with 1D velocity model just to try if I can track it. To do seismic reflection with just the sensor. Then you add few sensors, you move to proper elastic wave equation, so not acoustic, and you try to image it continuously.
I see. And you know how to do this, you know.
I need a modeler much better than me. That's my problem.
I see, and they're helping you.
Yeah.
So how do you calibrate your sensor, the frequency response of your sensor?
Sorry?
Frequency response of your sensor.
Okay, I didn't write it here, but if there's like, I don't know many papers from McCluskey that are doing this, and in our lab, Federico Pignalberi and Michele are among the guys that are doing this. So like, I didn't spend much, but there are 2 papers coming from our lab. One is already published and one is coming about how to track the frequency response of this sensor. I just show you the time response, but
In the data you have recorded so far, have you seen changes in amplitude and also in the shape of the waveform?
yes, I know it. I know it will come. So this is, I hope it doesn't broke, but like, okay, the black one, the black line is the change on the shape and its amplitude. The red one is my simulation. So you just forgot about the red one. And you see that continuously changes. Mostly, like the thing that changed most is the fact that layer thickness somehow is thickening. So of course the bouncing in the middle is different, but it's not all. I believe it's not all, and the tool, if we manage to raise the resolution, can account for, because this is a solution with, I mean, 10 points in the middle of across this fault zone. And you can see that it's not tracking that well, but the wave below is changing a lot. So this is why, for instance, using travel time cross correlation can be dangerous, while the geometry is evolving. Just because, because since I'm,
Also in the other direction.
I show you this.
Photography would be easier.
I show you this, but that's a really question from a modeling guy. You have to make it.
I'm not saying it's easy.
Yeah, I show you this. We actually acquired data. We actually acquired data with S waves in this direction, S wave in this direction, and longitudinal waves in 2 different points. The point is that then you have to move to modeling it, and I'm not good enough so far. We have the data. Like we are just the problem with software.
But you will be good.
Ah, thank you. Thank you, Mama. No, it's not.
Have a question. Do you have a plot of the frequency domain of your waves changing?
I have a lot I can show you, but like. Wait. I'm not sure if I have it on this experiment, but I don't know which that's. Late, sorry. No. I can show you late.
One last question from Julia.
So in a waveform figure, what is the first phase of the backline before you fit?
Sorry, once again.
Sorry, in a waveform figure, we can see some first phase of the back waveform. Maybe you didn't fit that phase, and you only fit the large amplitude waveform. Maybe. So what is the first phase? Large amplitude.
I didn't get it. I didn't get the question, but like.
He sees some faces before the arrival of.
Yeah, it's there. Yeah, it's there. Yeah, it's full of this. Like there's a and I don't think that come from surface wave. I think it's mode conversion of the fact that we have gauge still. So between still and gauge, you have huge mode conversion, mostly because you have grooves. Like to make the gauge stay there, we have grooves, and grooves make mode conversion everywhere. I don't know if there are surface waves. There are later on.
Yeah.
Okay.
Let's answer Michele again. And we will
Metti in tasca e poi non ho letto. Sì, solo un po'.
Can you hear me? Okay. So, good morning, I'm Giuseppe Volpe, and I'm going to talk about the role of clay in the nucleation of shallow slow slip. So, seismicity along subduction zones is mainly confined within 10 and 30 km of depth in a region known as the seismogenic zone. Above the seismogenic zone, subduction zones mainly accommodate deformation in a seismic way. This seismic deformation is mainly supported by the absence of regular seismicity as well by the low interseismic coupling observed along these shallow depths. The reason behind the seismic deformation of the shallowest portion of subduction megathrust can be found in the rocks characterizing the subduction interface. In fact, at shallow depths, we have 4 deep sediments, which are often rich in clay minerals such as smectite. Smectite, like other phyllosilicates, is a mineral characterized by frictional properties such as low friction, low healing rate, and velocity strengthening behavior that altogether favor aseismic deformation, hindering the typical dynamic acceleration of seismic slip. So, according to this framework, the shallowest region should deform solely by a seismic creep. However, it has been observed that these shallow regions, they do not deform solely by seismic creep, but they can also host the nucleation of peculiar seismic phenomena such as very low frequency earthquake, shallow slow slip, or also tsunami earthquake. And all these phenomena, the underlying mechanism behind these phenomena are still poorly understood because they cannot be easily explained by recurring this frictional framework. So, to understand why we can get these instabilities, we decided to characterize the frictional properties of monomeridionite, which is a smectite, using a double shell configuration with 2 layers of this monomeridionite gouge. We squeeze it, we shear it, and we measure the frictional properties using a biaxial apparatus. And we found that smectite is, as expected, frictionally weak. It has a very low friction coefficient, 0.23. Above 35 MPa of normal stress, it behaves in a ductile way. It shows a null healing rate. In fact, for all the normal stress tested, from 5 to 100 MPa, we did not observe any frictional strengthening upon reshear. And furthermore, it is strongly velocity strengthening with with positive values of A minus B that increase with increasing sliding velocity. So, all these data together point to an aseismic deformation of smectite, which is coherent. But if we look more in detail at what is happening during the formation of this material at very low velocity, approaching plate rates of few nanometers per second, and a relatively low stress when it's frictional, we observe that superimposed on the velocity strengthening trend, this is a down step, so with friction decreases with decreasing velocity, we observe this oscillation in shear stress. And if you look at them more in detail, they are frictional instabilities. These instabilities are characterized by a very small stress drop, few tens of kilopascals. They are characterized by very small peak slip velocity, few microns per second. And during the interseismic phase, the fault is not locked, it's not sticking, but is continuously creeping at very low velocity, few tens of nanometers per second, showing low interseismic coupling. But the occurrence of these instabilities in a velocity strengthening material is something unexpected that requires further investigations. And to do so, we developed a new experimental technique that allows to directly see what is happening on the fault surface by directly looking at that using a high-speed resolution camera. And if we couple mechanical data with visual data, we can see that in correspondence of the stress drop, so the dynamic phase of each stick slip cycle, you observe an abrupt change in fault reflectivity caught by the high-speed resolution camera. And so something is happening. And if we choose just one cycle and we look at the video, this is what is happening on the fault here. We are looking at something that look like a rupture. So we can see highlighted in red the nucleation phase where the rupture grows a millimeter per second. The nucleation phase is followed by a propagation phase, highlighted in blue, where the rupture front here maybe is propagating through the fault at 15 centimeters per second. Now, to get some more insights in the dynamic of these instabilities, we decide to relate changes in the fault reflectivity with the changes in the local stress of fault. So, what we notice that as soon as the rupture front passes through the fault, we choose just three points, we see that each point firstly experiences a big drop in stress to a minimum value that is followed by a gradual recovery of stress with time during the rupture, showing something like a self-healing behavior. But this rupture, the one that I show you that I analyzed together with you, is just one among several other ruptures we observe in our experiment. This is just one single experiment. Those are coming from this sequence, actually the 11 is above. But we can see that they are characterized by a slightly different rupture process. Some of them are nucleating in the top part, some in the middle, and some on the left side. But this is interesting because it's moving and seems to stop here. We cannot see actually a real breaking through rupture along the fault. With this method, we can also do another stuff. We can also trace the nucleation site of this event on the fault surface. Because remember, this is 5 by 5, it's a very small sample, and we have these huge complexities. So we can put stars and see, oh, look, these are the nucleation sites of these events. And what we can do more is also try to relate, since, as Michele said, even experimental faults have a structure, we can try to see if this nucleation site is occurring somewhere on the fault, specific place. And we can superimpose the fault structure on our videos, choose 2 other rupture, and we can see this is this black and white are, let's say, what we see in the rupture, on the fault surface. We can see, for instance, here, a small rupture that is nucleating here, seem very small, and then triggering another big one. Whereas here is nucleating here on the top, between this white and black region, and going all over the fault. We can do the same, trace, and see, look, those are, seems to nucleate in region where we have this transition, sharp transition from gray to black. If we do it systematically, we see that those are not randomly distributed on the fault, but we can see that in a considering a consecutive series of stick slip cycle, we see that the nucleation sites are not randomly distributed, but they seem to occur where we have this transition from white to black that represents a transition from a region with high stress heterogeneities. And furthermore, this stress heterogeneities is not random, but is related to the development of the inner fault zone structure, in particular our microstructure. This is just less than 5 millimeters thick. And this segmentation is actually derived, is produced by the intersection between the principal slipping zone, this really localized region here at the contact, and the currents of this reader shear that are segmenting the fault zone. So there is a really strong control exerted by fault zone structure on the fault slip behavior. So to summarize, we can see that clay-rich rocks have a complex frictional behavior that derives from the interplay between a local and a bulk frictional behavior. The bulk frictional behavior derives from the deformation on the wall fault zone and promotes low friction, low yielding rate, and velocity strengthening behavior, and therefore promote aseismic deformation, let's say the first order results. But there is also a local frictional behavior that derives from the deformation, at least from my interpretation, of small fault patches that, due to strain localization, stress heterogeneities, structural complexities, and maybe also alternative frictional properties, such as adhesion in this case, may develop a frictional behavior more prone to favor seismic nucleation, at least slow slip nucleation. And to conclude, our results support also recent findings suggesting a key role played by the frictionally weak clay-rich rocks in the nucleation of shallow slow slip, and also provide a possible new model for the nucleation of frictional instabilities in along velocity strengthening faults. And thank you for your attention.
Yeah, very interesting results. Can you put the sensors on the surface to monitor, for example, changes in normal stress and how they affect this response? Because, you know, the numerical model predicts.
Yes, yeah, we are trying to do this firstly starting on, as Chris, I have tons of backup slides. But for instance, here we did some experiment to try to characterize normal stress distribution on the fault surface using reflectivity, because it's easier. The problem to put sensor directly on the fault that we need the fault to be clear to see through the fault, because we need the transparent block. But in the meantime, we were trying to characterize this evolution. We are doing some normal stress steps with decreasing and increasing, and we see how this average gray level is simply the reflectivity, how it changes. And we were trying to give at each color of, for instance, here, we try to give normal stress values for each color of this. It's difficult, but what we were also trying to model, because we see there is a relation that scales with porosity. more stress you apply, more we have platelets, so they are not grains, so it's difficult. They are reorienting, reflecting more light, so it means that really attached and the stress is high. We were trying to do this. And to monitor also stress, we were thinking to apply, like as Michele was explaining, like like PZT sensor to see in each place of the fault what can be the stress. In a way, also measuring the stiffness and other parameters.
So with the current results, what's the you said structural stress, all sorts of conjecture, but what is the most likely conjecture you have?
Yes.
Yeah, wondering is, theoretical model with relationship, great strength in faults, with perturbation in normal stress, for example, can generate pseudo-surveillance, right? So I feel like this is one of the potential.
Yes, can be a possibility. For sure, I don't have the 100% sure answer for this question, but we can try to have some ideas. For sure, we have complex structural heterogeneities that favor normal stress changes on the fault. And frictional properties sometimes also changes with normal stress. So we can have a region where is more, let's say, velocity weakening with region is more velocity strengthening. Furthermore, we can also have, I talk about adhesion as a possible mechanism, because to have stick slip, we need at least creep slip, we need something to make the fault lock, or at least to decrease this velocity. And I was thinking can be like adhesion, because it's like a mechanism for make the fault regain strength during the small interseismic phase. And for instance, what we have done is doing some tests, and since adhesion is more efficient when you have two surfaces in contact that are clean and polished, we use this flat plexiglass block to put in the middle, and we put in between, one is flat and the other is with small quartz grains. And we see that this is the one flat, this is the one flat with quartz grains, and strange that with quartz friction is even weaker, but is maybe also grain rolling. So the monomerigonite cannot attach on the block. And when it can attach, we have stick slip. When not, it's stable sliding. We can also see that monomerigonite is one of the most adhesive minerals among a lot of natural minerals. And those results really resemble the one from some tribological work showing that when you put rubber on glass, if it is the surface is polished, you have stick slip. When you have grains, the friction is weaker and it's stable. Can be one of the hypotheses. And just to maybe anticipate another question, it's not a matter of the block, of the plexiglass block, because we did the experiment changing the roughness of the block, and the frictional behavior is always the same. We have the same evolution of A minus B, that can be the first order. So maybe the small stuff are changing the second, third order of frictional behavior, and also the microstructure are the same, so there is no change in how the fault look like changing the assembly.
Thanks. So these stick slip instabilities are very frequent, very rapid, right? It suggests a smaller scale, a length scale of the rupture. So is it possible that these ornitholonal riddle shear zones, riddle fractures, in the volume would be unstable, and then maybe the flat surface that is longer would be stable, and what you see is creep waves as after slip of faster ruptures in the volume?
There is a possibility, because actually we have some of the events, anyway, some of the events, I need to take these, where that like seems to appear from nowhere. So it's possible that some of them are also nucleating from the riddle and propagating through the full surface, since it is, let's say, flat, is more, maybe can be slightly velocity weakening. They can go through more easily. In the meantime, we have just the view of one part of the fault, because it should be a double direct shear configuration. We have just, let's say, we have two faults, but we have 4 interfaces, 2 for each gauge layer, and we are looking just one. So to have to understand better the complexity, we should, and there is Giacomo Pozzi, my co-supervisor, that now won an ERC that he wants to create a machine that can allow to see everything on this fault. So it's a matter of time, I hope.
And what's so special about the upper left corner there? Is it where you load from?
Here, this can be, since, so let's say, I'm not sure that when we apply the normal stress is really, I can show you a slide where maybe it's even easier. This is something that also maybe Michele can be interested. This is a video where we show how the fabric evolves with time. So this is the running phase, so we are seeing the fault at 10 micron per second, and we see in real time, this red line is synchronized. We see that how they are evolving. So we can see also that the stress is changing, and this upper region seems to be seems to be always loaded. Maybe because it's also a matter of geometries.
Where is the upper left corner on that video?
Here.
It's the same geometry.
It's the same. Okay.
Thank you, Greta. And you showed the propagation of the sweep, but it's almost almost like the pulse. Do you observe kind of the crack-like propagation?
So we should measure, to distinguish a pulse and a crack, we should measure the velocity of the rupture in the tail. And we cannot measure that. But what we can say, they are very slow. They are like 15 centimeter per second rupture velocity. I think they are pulses. But let's say another stuff can be used is this, that during the rupture itself, we have a recovery of stress. This means that this is, let's say, the tip and the region of the tail. Maybe since this is increasing means that the faults start decelerating. So we don't know the real velocity here. We should do particle tracking, and we are doing this. But should, let's say, pulse-like rather than a crack-like.
One last question before coffee. Okay, let's welcome back, everyone. So we'll now the pleasure welcome back. We'll now the pleasure to have Rolland speaking for a keynote.
All right. Well, I also want to thank Anthony and all the organizers for having this event. And I want to thank all of you, because it's really meetings like this and people like you that make life as a scientist doubly fun. So this is like science paradise for all of us, at least for me. So thank you. So you've seen these kind of diagrams multiple times during this meeting. Given that we've learned that in the natural system, we recognize great variability in fault behavior in plate boundary faults, including subduction zones and strike slip faults. So we've learned that there's sort of this complex puzzle and interaction of parts of the fault that makes big earthquakes, little earthquakes, different types of earthquakes, slow slip events, and some parts that slip more or less stably in that system. And so that means when we think about the earthquake cycle, right, which, since Reed 1910 and even before was recognized to be something related to elastic rebound, we have a fault that's stuck for interseismic long periods, and then it suddenly slips dynamically, and then the cycle begins. We now know that on the plate boundary, things are more complicated because of this variability in fault properties. And as you can see in Jean-Philippe's schematic diagram, illustrating the different phases of the earthquake cycle, that is being envisioned as being related to the interaction of these rate strengthening, so dominantly aseismic, and Chris gave us a nice overview as to what conditions relate to that, and Silvara gave further detail, and these rate weakening parts that make earthquakes. So it's kind of redundant to show this again, but very simplistically, right, the parts of a fault that make earthquakes are rate weakening in the sense that given a certain initial slip distance, this critical d sub c slip distance, if you're trying to accelerate a fault, so you slip it faster at some faster velocity v, the fault will eventually decay to a frictional strength that's less than at the lower velocity, so will get weaker. And if at the same time the loss of frictional resistance happens faster than the loss of elastic stress applied to the system, then we get an earthquake. And in contrast, the other end member view of a velocity strengthening system, if you try to accelerate the fault, it gets even stronger. So it really resists being accelerated, can't fail dynamically, unless you do things that kind of overcome that initial resistance. And Chris showed how, depending on how you run the experiments, these constants in the expressions, the rate state expressions that have been developed, can change with slip velocity. So everything's always more complicated than we think. But nonetheless, in a velocity strengthening system to first order, we can use that sort of behavior to predict if we do change stress, such as due to a coseismic event that changes stress on the surrounding fault, we would expect a sliding history, a velocity history of sliding that can represent post-seismic afterflood. So there's more going on in terms of in the whole earthquake cycle system in plate boundary faults. There's viscoelastic relaxation, pore fluid flow, etc. But we're really focusing, or I will focus in this talk, on the slip behavior on the fault and how these velocity weakening, velocity strengthening, seismic, aseismic portions of the system behave. And I want to focus just on one sort of basic idea in that, and this is related to what I refer to here as asperity erosion, that during the interseismic period, so following the initial post-seismic phase of afterslip, there's an evolution of the fault system that involves what is effectively a shrinking of the parts of the fault that are stuck, that are appearing to not slip, leading up to the next event. This next figure by Mafromatis et al. Tries to illustrate why we should expect that. So this is a very simple view of a velocity weakening asperity. You've seen examples of this very often, and then surrounded by velocity strengthening fault zone material. And especially if you have processes like thermal pressurization or other dynamic weakening processes, when you have a dynamic slip event, an earthquake, starting with that velocity strengthening patch, it will be able to break into the surrounding velocity strengthening part of the fault. And then with time, early, right after the event, slip will slow down, then we'll have after slip. And then as time progresses, the fault really, the parts of the fault that slip should shrink back, erode back to that inner asperity that in terms of its fault properties, persistent properties that make up that asperity behaves differently and stays frictionally locked. So what I want to do is essentially look at observations in the natural system that suggest that this is in fact a ubiquitous process. Okay? So that's what I'm going to try to do today. And I'm going to focus on just two examples. One, and I left both subduction zones and strike slip faults. I'm using a subduction zone and a strike slip fault, Alaska megathrust, and the Hayward fault as examples. And so in Alaska, we just recently had two magnitude 7.8 and 8.2 earthquakes in 2020. So we can examine the behavior of the fault zone just before these ruptures. So we can look at late interseismic coupling on the subduction thrust. And then I'm going to step to the Hayward fault, where we now have decades of observations of both aseismic slip and seismicity. And we can maybe in that record, and I hope to convince you that in that record we can see more or less direct evidence of this asperity shrinkage happening. Okay? All right, so the Alaska subduction zone, you may know, is composed of various rupture segments. One of the biggest earthquakes historically, 1964, ruptured here to the east. And then you can see here there were multiple magnitude 8 to 9 ruptures, pretty much all along the Alaska Aleutian arc. And those two earthquakes I mentioned were right here. And you can also see on here are the interseismic velocities, GPS measured horizontal motions that Jeff Reimel and colleagues had collected over the decades leading up to those recent earthquakes. So we have a record of crustal deformation that we can use to infer what is the coupling along the subduction thrust, the distribution of more or less rapidly slipping portions that presumably relates to the distribution of asperities that are fully frictionally locked, surrounded by parts of the fault that slip aseismically. So these are three very similar looking coupling models that Jeff and students and postdoc had developed over the years that all show sort of the same first order variation. As you go from east to west, the degree of coupling, so this is now in locking fraction where 1 means it's fully locked, where 0 means the plate boundary is slipping at the plate convergent long-term slip rate of the subduction thrust velocity. So there's that gradient from strong coupling as you extend into the 1964 coseismic rupture area, and then going to decreasing coupling to the west. So these two coupling models were published before the 2021 models. And you can see that the earthquakes, so these are the recent earthquakes that happened there, fall in an area of almost no inferred coupling. This last model looks different in that now suddenly the coupling is sort of at least at the right depth interval. So what this really shows is that inferring kinematically from geodetic coupling in a subduction zone is really hard because we have generally no geodetic data away from terrestrial, in this case, a relatively narrow peninsula and a few islands. So this is pretty much just a matter of lack of resolution. So in these two models here on the left, in addition to smoothing that is imposed to avoid overly rough models that are not really constrained by the data, there's an additional constraint of maximizing coupling towards the trench. And I think that was done partly sort of in the aftermath of the Tohoku earthquake, where coupling models in Northeast Japan all use just smoothing, Laplacian smoothing, and they all featured coupling at intermediate and deep depth in the subduction zone, and almost none in the part that eventually had 40 to 60 meters of slip, right? So then here the constraint was make coupling strongest at the trench and then gradate it away from there. In this model, the constraint was using a Gaussian, so kind of going back to a model in which you have peak coupling somewhere in the middle, decaying to the edges, which fit the data equally well. So given that these models and these models fit the data equally well, that just tells you that maybe we can't say so much about details of coupling from these geodetic inversions. To improve that, we will need seafloor geodesy to have data that's closer to the parts of the fault that actually produce earthquakes. So an alternate way of modeling coupling on a subduction zone is taking that concept of these maybe persistent, fully locked asperities surrounding by an aseismically slipping fault, where rather than doing an inversion, a kinematic inversion for distributed slip, we're saying, let's lock the parts of the fault that we know have slipped in recent earthquakes, right? And then solve for the slip rates surrounding those, given that depending on how much of the plate boundary is locked and where it is locked, the slip rate surrounding that will be varying based on the loading stresses applied to the system and the pinning effect of that asperity. So what you see in this schematic diagram, what's labeled here as stress shadow, is essentially if you load the system due to plate tectonic convergence, slip down dip, up dip of a locked patch, the coupling will be increased, so there will be less slip rate, just because of this shadow effect of the, or pinning effect of that locked asperity. Okay? So does that make sense physically, right? And the way you do this is essentially implement a model in which you lock parts of the fault where you had earthquakes, and then you solve with a stress boundary condition using boundary and element models or other approaches where the slip occurs. So there's not even frictionless model. The fault will just slip the way a velocity strengthening fault would eventually, as much as it wants to, as fast as it wants to relieve all the shear stress added to it. Okay? Okay, so when we do that, we need to know where earthquakes have happened. So these are various papers characterizing slip in the major earthquakes that have happened since the 1960s or so in this area, including 1938, 1946. This is a kind of enigmatic tsunami earthquake that seismically looked rather small, it's 7 point something, but based on the tsunami data was a magnitude 8.6. And then the most recent earthquakes right here. So if we do that, so here we just take the historical earthquakes, the really big ones, 64, 38, 46, and 48, and we are doing this calculation, so we fully lock these and solve for the slip rate surrounding them. So the further away you are from these left section, the higher your slip rate will be. So the coupling factor will go up close to these asperities, or the slip rate, and the way you model this is with a backslip approach, varies accordingly. So when we do that and we look at the fit to the data, you may have a hard time seeing to what degree the modeled vectors, the right vectors, fit the right ones, but you way over predict the landward velocity, right? So the subducting plate is dragging the overriding plate too much. There's too much coupling in that system, okay? So that suggests that these fully locked asperities have to be smaller than the extent of the ruptures that were inferred from these models that I showed you in the previous slide. So then let's just shrink them, right? So we make them smaller, about a quarter of the size they had. And then you're starting to approach out here in the east what the GPS velocities match, the model match the observed. I haven't yet locked the ruptures that just happened recently, so if I lock those as well, only in their inner portion, then we're starting to match the data quite well, and actually just as good as those smooth coupling models that were previously published. But in this case, we don't just let the data and smoothing regularization guide the kind of models that we develop, but we're taking this idea of asperities being a real thing, being persistent, and then finding that we need to make these really small to match the surface deformation. One thing that's interesting, and it's partly limited what we can say by the geodetic data out here being quite sparse, but this 1946 event, right, that was an 8.6. If we just take that away altogether, you actually fit the data even a little bit better. So, you know, maybe where the tsunami earthquake was not yet coupled in the decades before, in the last few decades. So that's an interesting aspect.
Do you mind?
Chris, no, please do.
So what about just reducing the coupling? Instead of making them smaller, let them slip a little bit. Is that something you would
You could do that too, but then I would give up on my sort of idea that asperities are a real thing, and there is such a thing as fully frictionally locked faults. It's an end-member view, but it's a really great question to ask, because yes, of course, I could just slip everything a little bit, and then it would look like those smooth models again. But that would sort of go away from that premise that there is a thing as real locking, which I think is a real thing. We can infer that also from things like seismicity and tremor and all those things. Any other questions? Yeah.
What if you put the aftershock distribution? Is that consistent with?
I will get to the afterslip next. Yeah. Even though I can't tell you if it's consistent more with a little asperity than a big one.
Could I ask just a very quick so you take the asperity prescribed from the slip model of big event, or you actually allow to shrink it further to match during your inversion process?
So right now I'm just saying I have the deformation before, just now, these recent earthquakes, and I'm just looking at how small do I have to make them to match the geodetic data. How that happens with time, I can't address yet, right? For that, we really need more information.
More time also.
Yeah, so the big message is to be able to actually see this in action, you need data that spans a lot of time. Because this is not a precursory process, this is an interseismic duration of the interseismic process. All right. Okay, so Yoshi asked about afterslip. So for these recent earthquakes, given that we have continuous GPS stations in the area, we can also model the afterslip, right? And so what you see here are two ways of modeling the afterslip. One is kinematic, so we're just solving for the distribution of creep, and this is just for the first 90-day period. So there was substantial rapid deformation that indicates that afterslip, starting immediately after the earthquake, was rapid and ubiquitous. And you can see from that, while it's heavily smooth, it seems to be occurring both up dip and down dip and laterally of the rupture. The model on the right is a stress-driven model. So this is where I'm using Silva-Barbeau's unicycle model that essentially implements that equation that I showed you earlier, which you'll see in just a sec here. And we solve for the evolving slip rate as a function of time and space surrounding the rupture that just happened. So it's the co-seismic stress change that essentially gets parameterized in a way that with an appropriate choice of our A minus B, or really just A value in that simple expression, matches the deformation data. So this is that equation again. So essentially optimizing from the data to match the time series of these GPS stations, we can find the initial V0 velocity and the rate state constant term that best matches the data. And so at least in this case, and it doesn't always work that nicely, the stress-driven, more physical model, right, that actually takes the physics of stress change-driven slow slip, velocity strengthening slip into consideration, matches the data almost as well as the kinematic inversion that isn't concerned at all about that slip happening in places where it could happen, right? I could have found slip somewhere far away from the rupture that maybe the data prefer, but seems to be unlikely given the physics of the problem. And as is often observed, the decay of the slip, so this is in red, the cumulative, in blue, the cumulative afterslip, in its temporal behavior is very similar to the cumulative number of aftershocks. This doesn't tell you too much. This includes aftershocks that are actually quite far away, because ultimately aftershocks driven by an earthquake in the volume and aftershocks driven by aseismic slip on a fault will have a very similar log decay, right, in both the expressions that Jim Dietrich came up with for the respective problems. Importantly, the moment released in the earthquakes, in this case, is 2 orders of magnitude less than the moment released in the afterslip model, right? So definitely that deformation we see is essentially 100% aseismic. The aftershocks just kind of provide a little bit of noise to that system. Okay, so at this point, I've shown you this case for if we use this model of persistent asperities and want to model interseismic deformation with that approach, I have to make my fully locked patches quite small, much smaller, about 1/4 of the size of what was thought to be the slip zone of these earthquakes to match the surface deformation data. And from the afterslip observation, we have some constraints of the portion of the megathrust surrounding both down dip laterally and up dip of the fault, apparently being velocity strengthening, having these frictional properties that we associate with aseismic slip and stability in the fault system. Now, over 20 years ago, we found something very, very similar when we tried to model the coupling on the subduction thrust much further west in Kamchatka using the same kind of surface velocities. This is a smooth, Laplacian smooth kinematic inversions. And then I ran into the same problem here, where if we lock all the known coseismic slip zone, or thought to be known slip zones, we way over predict the coupling. All the modeled velocities are much more landward, much faster landward than the observed. And again, by shrinking all the asperities down to about 1/4, which is sort of what we did back then, we start matching the data well and almost as well as in this kinematic inversion. And similarly, in Japan, using interseismic velocities inferred from continuous GPS measurements in Japan around 2009, taking the slip zones of known historical moderate to large events in Japan, Kai Johnson found that he had to make those again quite small. And I remember he emailed me and was like, you know, I just saw your paper on Kamchatka, and when I went through this exercise using a very similar modeling approach, I also find something like 25% matches quite well. Now, the GSI network, the continuous network here, had been around for decades. So when Kai went through the same exercise using the inferred velocity from the GPS time series a decade earlier, he found he needed to couple the megathrust substantially more. So here there was apparently a decadal scale, right, over about 20-year time period, decrease in landward velocities, and increase in landward velocities, and decrease in coupling as a function of time over that kind of decadal time scale. So this is a really unique observation that we just haven't been able to do anywhere else, because we don't have the same kind of stable decadal existing GPS network. We're beginning to, right, in many areas. So it's going to be interesting to see if this is something that's common and ubiquitous or an anomaly. Okay, so much for subduction zones. Any questions before I move on to the Hayward fault? Yeah.
Rolland, if you can go back to the slide, it appears that the fitting for the data is better for 2009.
It doesn't want me to go back. What's going on? There we go. Sorry.
The fitting and the P is better than C. Does it really says they require more coupling?
So more coupling in 1998 than 2009. So with time, the coupling is less, or I should really say the asperities shrink, and that allows the surrounding areas to slip more
I
slowly.
think the question is about the fit to the data is much poorer.
The data is different.
The fit is different, and so
It's different data. This is just a model that using the same idea. You're fixing where you couple, and then you adjust the size of where you have coupling, right? So there is, still some misfit, but overall, if you look at this, you fit the data similarly well in these cases, but the data that is being modeled is different here and here, right? This is a time-dependent velocity now. There's no such thing as steady interseismic deformation rates.
Just saying the fitting of C is better. Looks like.
I don't have the statistics. Looking at this, I would say it's very similar, but we would have to look at the paper to get the WRMS or chi-square values, right? But it's fair enough to ask. Yeah. Okay.
Thank you. Do you think also that this EBS change that you are observing can be also explained, but not to things that are happening in the interface, but could be some change in the load also that happened before?
Yeah.
Rather than something in the interface.
Even though if it's a change in the load, right, in the plate convergence, then you should see that in the far field, right? So I think if people have suggested there could be, changes in plate motion rate, but that's hard to do, right? It's both hard to do physically, and it's hard to do that without violating the data somewhere else. So, but nonetheless, that's absolutely right. We could also, soften the Forearc, right? These are all perfectly elastic representations of the Earth. We know that's not true too. So there's probably multiple ways one could, produce something like this. So it's important to ask those questions. All right, on to up.
Yes. So be fair to the data. I like that diagram very much, right? But what the data require is a decrease of the overall coupling, right? The fact that it can be interpreted by shrinking of the asperities is one possible explanation, but it's not required by the data themselves, right? There could be
really important, right? So this is a model. So this is trying to match this apparent acceleration with a model that tries to do so by changing the size of the locked asperities. What the data are really saying, and I'll be showing you a figure that shows, another way of modeling that or seeing that. It just shows that the overall creep rate, right, the slip on these areas surrounding it is allowed to be faster, right? That's really what we're seeing. We're not actually seeing the asperities shrinking. The only way you would be able to see shrinking of asperities if you have measurements that will allow you to actually image the edges of these locked sections. So that's really important, a very important consideration. And in the next part of the talk, I never see a shrinking asperity. I only see changing slow slip rates on the parts of the fault that presumably are surrounding the locked parts. Yeah?
But it could be also explained by other processes, not necessarily something that occurs on the interface, but also maybe like viscous.
Yeah, exactly. Right.
Relaxation.
Yeah. Yeah, so everybody keep that in mind. There are many, many ways in which you can make the Earth deform in the way we observe it. And we always need to think about what in the end makes the most sense based on the physics, based on your knowledge and intuition about how plate boundaries work. Matteo?
Yeah, so it can only go one way, meaning the asperity can only shrink, and then you have big rupture, and then you set up, or could it go both?
Yeah, so far, right, I'm focusing on shrinking because that very simple model I showed you at the beginning to sort of set the stage, this idea that dynamic weakening makes ruptures always be bigger than the actual velocity weakening parts of a fault, and then in that model view, it always has to shrink back. I'm sure we can come up with a model in which as things slow down, they heal up more, and then maybe asperities could grow, right, as you go through the earthquake cycle. And then we have, this observation of the asperities actually or plausibly shrinking, and we have the observation from Alaska, from Kamchatka, and Northeast Japan that the apparently fully locked portions of the plate boundary are always much smaller than the extent of the co-seismic slip that had occurred some time ago.
Roland, just to follow up, is dynamic weakening really required? I mean,
No. So in, the dynamic weakening is, I'm partly relying, and I'll show if I have time, an animation, in the kind of models that Nadia's group developed. Dynamic weakening is an important part. Thermal pressurization allows ruptures to do that. You can also do it, there are also models that you can find where you can do that with appropriate choices of A minus B and D sub C. So you do not need dynamic weakening. But we know dynamic weakening is a real important process, right? In terms of how we understand plate boundary slip to happen. Yes?
So my question was, because we know that this is in the preparatory phase to Tohoku, which famously had a decades-long kind of acceleration, I've seen. And I was wondering if it's ever, this kind of asperity shrinking was something that we could actually see in true interseismic time, away from any kind of bigger.
That's a really quick question, right? In the way, we only see the last few decades, the earthquake recurrence time is on the order of 500-600 years or so. We don't have observations for much of the period. In this model, the idea is that this is happening, throughout the earthquake interseismic period following the initial afterslip. So you have afterslip, let that fully decay, and then over hundreds of years, you get this retreat to the locked asperity. But I would love to have data to actually show that. So that's something to look for. Yep.
Well, having just that, what you said in mind, you could observe or you could make some sense of the rate of shrinkage over this decadal period that you are looking at. If you can extrapolate back into the interseismic period or forward, assuming these other, would that make sense? Would it wipe out the entire asperity if you would assume that?
If you just keep going, then, well, it's wherever your velocity weakening part is, right? If that's a true...
But velocity weakening part could also be eroded. It's just...
Maybe, right. I mean, I'm sort of going with the premise that there's something special about that the velocity strengthening and the velocity weakening are different based on persistent property, right? Lithology, structure, and we had debates about that earlier, right? Is it mineralogy? Is it pore pressure, which would be temporally variable? Is it fault zone structure, etc.?
Are there places on Earth where the deep edge of the lock zone is inland or very close to the coast so that we can track these variations through time?
So there are places where there is data over, further into the zone, like Nicoya in Costa Rica, or in Sumatra, we have these islands. So there you have the ability, again, if you have data spanning enough time, that we should start seeing that as you accumulate data. It depends sort of on that combination of recurrence interval and where your measurements are. Yeah. And then maybe I should go on, because otherwise we'll just skip to the end and keep talking, which is actually great. In a way, we should just keep going, because this is really fun. But let's spend a little bit of time on the Hayward fault, right? So now we're looking at a strike-slip fault in the Bay Area, in the most urban part of the San Andreas fault system in Northern California. It's just next to the San Andreas fault, which carries about 25 millimeters per year of the 40 millimeter per year plate boundary budget. The Hayward fault has a slip rate of about 10 millimeters per year. It had a big earthquake. It was actually called the Great San Francisco Earthquake of 1868. It destroyed big parts of San Francisco, actually the same parts that then got ruined by the 1906 earthquake. and all the few communities that existed in the East Bay at that time. It was roughly a magnitude 7 earthquake. From paleoseismology, we know that earthquakes that produce similar features in trench exposures along the southern part of the Hayward Fault recur on average every 150, 160 years, depending on how far back in the paleoseismic record we take estimates into consideration. The earthquake happened 156 years ago, so we're actually past the average recurrence interval. So we're definitely very late in the earthquake cycle. In the Hayward Fault, in the probabilistic hazard models for California, is sort of at the very top rank together with the southernmost strand of the San Andreas Fault. So I assume in my lifetime we'll have a big earthquake. But the Hayward Fault also creeps. It has aseismic slip, and we can see it right at the surface. We don't even need to make models. And so this is a famous curve in Hayward, and here are pictures that people took over the decades, and you can see that curve is incrementally offset, on average about 5 millimeters per year with time. And all along the Hayward Fault, from San Pablo Bay, where the Hayward Fault goes underwater, down to the end in Fremont, we see evidence of creep like that. That includes the football stadium in Berkeley that you may have heard about. We set up GPS receivers at the four corners here, and after just a few years, we could see that this side of the fault moved relative to the station here on the west side at a rate of about 4 millimeters per year, which is a little less than half of the long-term geologic slip rate. And using various kinds of surveying techniques, alignment arrays, field measurements, creep meters, and other ways of measuring creep along the fault, already by the 1990s, we knew that creep is sort of 5 millimeters per year plus minus 2-3 millimeters per year. We can also use InSAR. Romain gave us a nice overview how InSAR provides us these really dense measurements right at the fault of the fault slip itself, and the gradients of deformation away from the fault that help us then understand how deep that creep extends and how fast it is in the subsurface. And here you can see the football stadium, nice change in line of sight velocity across it. Here's the mapped surface trace. These red patches are actually active slow-moving landslides, sort of adding to the hazard that we face, and I live somewhere right up there. And then we have repeating earthquakes. You've heard about those a little bit too, right? So repeating earthquakes are events that can be shown to have extremely similar waveforms. For some of them, where the data is good enough, you can actually show that their slip zone overlaps nearly completely. They can sometimes have variable magnitude in interesting ways, but we understand them, the ones that are true repeaters, as being stuck patches on an otherwise creeping fault that are driven to such frequent failure every few years because of that rapid stressing, that rapid loading. So if we have a lot of these on a fault plane, we can take a bunch here in this little square and look at when they occurred and then group them and infer using a moment to slip increment relationship what the slip history is seismically at the repeater, and then using this idea that they're driven by surrounding creep, infer a aseismic slip history of the surrounding fault. And by doing so for these patches where we have multiple repeaters, we can produce for each of these fault slip patches a slip history that we think is a fault creep history on the fault. Right, so then we can make maps of slip rate or slip over a certain time as a function of space and time. And so here's shown, this is Takaaki Taira who did that. Wherever we have enough repeaters in a box, and we have here from 1992 to 2010, we can infer a slip rate using this idea. And you can see, if you look at the scale, the subsurface creep rates are on the order, again, of about 5 millimeters per year with some variability. So this is cool, right? Because here we actually now look on the fault. We're not limited by our resolution limitations, by only having surface deformation measurements, but we can actually look on the fault and see where slip is occurring. So we take regional GPS data to get at the far field gradient, InSAR data, field measurements, creep meters, alignment array measurements, and the repeating earthquakes. Those are data, our slip constraints. And then we do the kind of modeling that Romain showed us many nice examples of, and infer what is the distribution of creep rate in the subsurface. And essentially what you see is creep extends at that about 5 millimeters per year down to about 4 or 5 millimeters per year here in the northwest. It seems to extend throughout much of the seismogenic zone. And then down here we have portions that effectively don't slip at all. So this is presumably the core asperity of what slipped in 1868, and we should be worried about slipping again in the next earthquake. Over the decades, there have been various studies, even more than ones than I'm showing here, with variable results depending on which data were used, what kind of modeling approach was used. But they all agree that there is part of the fault where essentially there's probably no slip at all. And the slip deficit or moment deficit rate that we get from this suggests that after about 100 years, you accumulate enough slip deficit to produce a 6.8 earthquake. And so with none having happened since 156 years ago, we have enough slip deficit built up to make an earthquake. So nothing time dependent yet. We'll get to that. And this is the kind of modeling that I showed you earlier, where now rather than doing an inversion, such as in this case, which is very similar to these previous models, we use this approach of coupling portions of the fault and then solving for the slip rate using stress boundary conditions. If you don't couple anything, you only pin it on these sides, you get high straits in the middle, right? And then you go to zero slip rate at the edges. If you put in locked patches, so these are now imposed, and you solve for the creep rate reduces because of that stress shadow effect. And you can then see as you grow this locked zone and move it around how the slip evolves. And again, this model, where about 20% of the fault surface are fully locked and the rest is allowed to slip based on the interseismic loading, matches the data just as well as this. So we do have time series. So in this study with Manu Shirsei, we had 18 years of InSAR data and also GPS data. So we can also make a time-dependent model. So this animation here shows the accumulation of creep as a function of time, and also in red the occurrence of repeating earthquakes, and in blue other microseismicity over the years. And here on the right, each patch with a time series next to it shows the slip history. Maybe you can see down here there's sort of a flat section, and then in 1996, sudden acceleration. That's that creep recovery that Romain showed us, where after the Loma Prieta earthquake, this southernmost patch didn't slip at all. And then in 1996, there was a 2.5 centimeter creep event in the upper 3 kilometers or so, catching up with the slip history. Oh, and then this shows the contour lines here. So in the background is the coupling model. The contour lines with this scale right here shows the acceleration. If you fit an acceleration term, right, an exponential term to the data, and there's variability, then this would be where you get acceleration of creep. And now we have Sentinel. So there was a gap in InSAR coverage between 2010 and Sentinel coming into action in 2015. This is the model using the 18 years of data prior to 2010. This is a coupling model made more recently using the Sentinel data. And you can see there is faster slip here and here. And if this is the lock disparity, it's definitely smaller than it was here. And there's other variability that's probably more due to noise in the data and the challenge of inverting for coupling at depth than anything else. But the indication from these data is the fault is now less coupled, creeps more rapidly than it was before. If we take the surface creep measurements, and I'm just simply dividing them up at 2010, which was where we had that gap in acquisition in the InSAR data, so 20 years of data prior to 2010 versus since 2010, you can see that almost all the earlier measurements here are at a lower velocity, the cyan dots, than before. And this shows just pre versus post. You know, many of these sites have a faster rate later. And if we divide up the repeating earthquakes similarly into pre-2010, post-2010, and then look at the difference in percent, you can see almost all the patches where there were enough repeaters both before and after that arbitrary dividing line, they now apparently have a faster slip rate. And if we take all the repeaters in here, in the northern Hayward Fault, and here in the southern Hayward Fault, that gives us a lot of them. Then we can actually make a cumulative slip time series. And you can see there's a subtle, but I think quite visible acceleration that we can make out in these data. Okay. So we have three different data types: InSAR data, surface creep measurements, and repeating earthquakes, completely independent, that all seem to suggest that to first order, the fault is slipping a bit faster in the last 10 years or so. The Hayward Fault is not the only creeping fault. Just to the south is the Calaveras Fault. It also had moderate earthquakes, 1984, 1988. Creeps even faster. We can play that same game with the repeating earthquakes. So Hayward Fault ends here, Calaveras Fault starts here. Pre-2010, post-change, the Calaveras Fault slowed down. Okay? And if we again divide up the fault into two sections, northern central Calaveras, southern central Calaveras, this is southern, this is northern, you can see that since 1984, when we have cataloged events, there has been a continuous decrease. 1984 was the biggest earthquake on the Calaveras Fault that we've had, a magnitude 6.2. So this looks like the afterslip phase continued for about 40 years of this decaying afterslip transient. So that in itself is interesting, even though it isn't yet in the asperity shrinking phase, right? Very clearly. Okay, so this reminds us of what we saw in Japan, right? So these are now from the GPS velocity accelerations, the megathrust slip accelerations that Andreas Mafromatis, Paul Uchida-san, and Kai Johnson inferred from both the GPS data and from repeating earthquakes that Naoki Uchida had been studying for a long time, that similar to the repeating earthquakes on the Hayward Fault, show accelerations down dip and surrounding the Tohoku rupture, and decelerations here to the north. And this is from a more recent paper by Lou Maril and Suke and colleagues that found, very comparable results, after having reprocessed very carefully the GPS data. So this is really a very solid observation. And then the inference is mapping that into explaining that by changes in slip rate on the megathrust, which then, as I showed you earlier, Kai tried to explain physically by making the asperities smaller, because the smaller the asperities get, if the background plate tectonic loading is the same, then the slip rate will increase, right? So increasing slip rate on the fault surrounding the locked patches is directly consistent with shrinking of the locked patches, or is a needed consequence, right? If you shrink asperities, then if you want to keep the creep rate steady, you would have to reduce the loading rate, meaning plate tectonic convergence or loading. Okay, so Kai, who's working with us on this, made a model of the shrinking asperity, and he had to, make some assumptions. We know almost nothing about 1868. So he made a rupture that roughly matches the extent of the rupture based on where it's been observed at the surface. There's a study by Paul Siegel and LNU using triangulation data to infer how long that rupture was. And then he applies using a model that Camilla Catania had developed with Paul to impose this shrinking asperity. So this now shows, starting about 40 years after the coseismic imposed slip, you can see this decreasing asperity size and increasing slip rate surrounding this patch. And this is just a forward model. I just ran a few models to see what this would look like if we assume that this is what's happening. And from that model, the difference between early and late creep rates along the fault sort of has the first order pattern here. It's probably too much. There's probably too much acceleration here. And the comparison with the accelerations from the repeating earthquakes, roughly matches that what we found from that. So to first order, a model like that seems to do the trick to produce what we observed, these accelerations. Okay. So this is now a model that Chunli Zheng and Nadia Lapusta published a while ago. They were interested in a band of seismicity deep on the San Jacinto fault. And so they were actually not even interested in the shallow creep here at all. But when I looked at this paper more carefully, I found that if you compare their early interseismic with their late interseismic model, you can see that the fully, non-slipping locked asperity, also the locking depth at the top, decreased. So in addition to what they were interested in happening down here, there's also this change in slip here. And this is a model with dynamic weakening, velocity weakening asperity, velocity strengthening material in the surrounding. So this model is sort of a rate state, state-of-the-art model with many, many earthquake cycles that produces the kind of thing that I think we're seeing. And in that model, I talked to Chimla at the SCEC meeting a few weeks ago. I was like, don't you remember in your supplement there's that figure that shows this dashed line? This is the pre-earthquake, so in the very late stage of the earthquake cycle, and you can see the slip rate here at the surface is about double the slip rate that it was after slip decays to sort of that lowest slip rate value early in the interseismic. So he was surprised by that because he didn't remember that was the case. Okay, so that's it. I made the case for frictionally locked co-asperities, if that's the right way of thinking about what coupling variations on a plate boundary fault are due to. Late in the earthquake cycle that we observe in a number of subduction zones, Alaska, Kamchatka, northeastern China, seem to be systematically smaller than the extent of those ruptures as they had been modeled previously. On the Hayward fault, and even more convincingly maybe prior to the Tohoku earthquake, they're these decadal, so you need tens of years of data accelerations in apparent fault creep that would be consistent with the idea that during that time, during those decades, asperities started getting smaller and smaller, allowing the surrounding fault to slip faster and faster. And so that would then suggest that a natural component of the interseismic period of the earthquake cycle, at least on these faults and maybe on more to be determined, includes this asperity shrinking process, that ruptures often extend away from what is their internal core velocity weakening asperity source, and then eventually shrink back to that through the earthquake cycle. So right now this is just an idea, but I would love to hear more discussion and your questions on that. So thank you.
Thanks for the very interesting talk. I was just, so returning back to the erosion, so as you also showed in the Jan Lapusta, so what was eroded in the later stages, I guess, of the interseismic cycle, what was eroded was the velocity weakening patch. So in principle, you could have frustrated instabilities prior to Earth, so slow slip events in this eroded part of the velocity weakening patch that would register as an accelerated slow slip, which is not necessarily a reflection of shrinkage of, shrinkage could be much slower process to account for this gradual acceleration of slip just due to the change of the coupling on the fault. So that's what I know what you
Yeah, I mean, right in that something has to shrink to allow the creep up here to get faster, unless you also add loading rate, right? There was an earlier question, could it also be that the far field loading would be faster, right? And that could be, right? We see on the, remember the Calaveras fault has a 40-year afterslip transient. That actually seems awfully long, right? Decay times of afterslip tend to be on the order of a month or so. So I'm actually wondering if that's to also modest but still visible in that creep record viscoelastic relaxation that has longer relaxation times. And something that we talked about modeling a bit more carefully. So there might be more going on there, but the Hayward fault is just the opposite. And we did look at models of viscoelastic relaxation from 1906 and 1989, models by Fred Politz. Those would produce the opposite change in creep rate. They wouldn't accelerate the fault now, they would actually lead to a decay of slip rate. Michele, and then in the back, and then
thank you, Rolland, for the presentation. I have just one question. Like, is there a single phenomenon, or if you have to pick one phenomenon that will say the model of shrinking asperity can't not work because I observed it? What would you pick?
You know, I would bet this won't work everywhere, right? Nature is just not that way. You know, so far, you know, with the examples I showed you, this sort of way of modeling the subduction zone that seems to require that if you have fully locked patches, that they're much smaller than the extent of earthquakes, that I think might be ubiquitous. But because there are so many other things that happen in plate boundaries, right, as we discussed, other earthquake cycle processes, other kind of frictional physics, pore pressure changes that influence faults, those are all probably real processes and would make everything messier. The Earth is always messier than our models, so, and as we saw even in the lab, things are so much messier than the simple theory, so so my guess would be that it's the latter. Yeah. Yeah.
Thank you for the presentation and the overview. If we focus on the Japan offshore, you show landward acceleration and deceleration along the margin. And based on the numerical simulation, can we infer the timing of the seismic cycle depending on accelerating or decelerating according to your?
Oh, that's a great question. So from the acceleration we see specifically in Japan, right? What if we back project that? Does that get us to 600 years ago? Ooh, what's happening The answer is I don't know. I don't recall. Maybe Anne would know because they've done determined accelerations, but I don't know if you guys checked on, well, what was the starting point?
The acceleration?
Yeah.
It's very difficult to assess because, from before 2003, the data is pretty...
Right, there's almost no data, but if you just take the acceleration that was measured and you just go backwards in time, right? The model I showed you for the Hayward fault, that starts only 40 years after the 1868 earthquake, and given that I can now scroll, if you look at the...
Can we use this acceleration and deceleration pattern that is measured nowadays with geodetic into something that is useful to constrain the timing of the seismic cycle locally?
Say that again.
So now we are measuring in many places this acceleration with respect to the standard interseismic period, right?
Yeah.
And the question is, can we use this type of signal to probe the timing of the seismic cycle at that point?
Oh, that's obviously the key question, right? What are the implications of this? Some people say, oh, that's a precursor, right? That means the Hayward fault earthquake is just as due as the Tohoku earthquake was, just 10 years after this acceleration was evident in the GPS rugged. In this model view, the answer would no. In this model view, the answer is no. This shows the acceleration since 1980 in the model. I have a similar plot somewhere that goes back to the 1940s, right? This just keeps going and going and going, and so no, it's not something that you can use to better forecast the earthquake. It does imply, right, as these asperities are shrinking, the creeping parts are growing and accelerating, the loading rate, the stressing rate will increase, right? So if stressing rate gets you closer to ultimately having failure, it definitely brings us closer, but because it's a process that's continuous, it wouldn't help you with the prediction business. So Chris is next, and then Daisuke.
Rolland, really nice talk. Thank you very much. I've got a kind of fundamental point that could almost be so fundamental that it's semantic. But you say locked. And when I hear locked, I think the velocity really is zero, the shear velocity. But for every lab experiment I can think of where we have good, careful measurements, I don't mean anything older than 50 years ago, because where you have local, careful measurements, you only need about 10% of the eventual strength to start the creep rate. So if you can say to me, well, when I say locked, I just mean it's moving at less than 100 nanometer per second, okay, then maybe I don't care anymore. But especially when you talk about shrinking of a locked asperity, I think to myself, yeah, but what if it's just accelerating from some incredibly low, what if it's accelerating from 10 to 30 to 100 nanometers per second? So,
No, when you made that point also about Andy Reina's model, right, which assumes there's always slip going on. In this view of the fault zone, when I say frictionally locked, I do mean locked, right? And maybe in reality there's still some strain in the fault zone, but right where we have subduction zones and faults that are fully locked, we essentially see nothing on the fault. Geodetically, there's no microseismicity, there's no evidence that anything is moving. As soon as we have a creeping fault, more than 2-3 millimeters per year, then usually there's microseismicity, a few repeating earthquakes.
For materials, because if you look at tremologists and what they do, any mechanism involves a crystal plastic, a vacancy point diffusion model. They're all asymmetric to the point where as soon as you add a little bit of shear stress, it starts to go.
I mean, the challenge is, right, the bigger the locked part of the fault is, the deeper you are in the locked part, and I'm saying locked, the lower the stressing rate too, right? Because you're further away from where you have deep loading stressing the system. So I think you're right, this black and white view may be dangerous given what we understand about what we learn in the lab. But when I say frictionally locked, I mean frictionally locked. And then the rest is just slipping, or coupling is just how fast you slip. Are we out of time?
Last question.
That's okay.
And Estelle, if you want to take your slides.
My question is, how to distinguish the intents and the precursory preset? Because both of them are the anomaly in the slip depth rate before the occurrence of the negative pathways.
Oh, dangerous question, right? I mean, what do we know about precursory slip? We have a few observations of that happening. We know from the lab there should be some nucleation acceleration of some sort. This is sort of the end member case of just a full cycle change in the mechanical behavior of the plate boundary. So it's not a precursor, but I think the short answer is we wouldn't be able to. You would just assume that a real precursor is shorter duration, more transient in nature. There's an onset of it, and then it leads up to whatever the rupture is. But I've seen enough, evidence that so far in nature we haven't seen a ubiquitous evidence of that being something that is resolvable with our current observations as being something that we should expect. Yeah. But we might be mistaking one. Maybe the pre-Tohoku acceleration over the decades was just as precursory as the acceleration over a few months that Aicharo saw with the seismicity. All right, thank you.
Okay. It's okay. You can hear me. It's okay. Okay, so hello everyone. So my name is Estelle Neyrinck. I'm a PhD student from the University of Strasbourg. And I'm really happy to see all of you and to meet you. So today I will present you the slow slip event cycle along the Izmit segment of the North Anatolian fault using InSAR data. So we will continue with strike slip fault. So just a reminder. So the North Anatolian fault is this huge 1,600 kilometer long right lateral strike slip fault on the north side of the Turkey, separating the Eurasia and the Anatolia plates with a loading rate about 24 millimeters per year. And as Romain Jolivet explained yesterday, this fault is really famous because we have this propagation of main earthquakes with magnitude higher than 6.7 from the east part to the west, so with the Izmit Pasha segment here. But today we will focus on the two last events in 1999 in Izmit and Giuseppe. So if we zoom in, here you have a map with the earthquakes since 1999, and you have in red the rupture caused by both earthquakes. So the post-seismic and post-seismic deformation have been widely studied for these earthquakes, and we will try to understand what is happening along the Izmit segment, which is just here. Okay, and the idea is to see what is happening 20 years after the earthquake. So if we try to see just a few years after the earthquake, so you have this paper from Shane et al. In 2016. They used InSAR data. So here, just to localize everything, you have the eastern part of the Marmara Sea, the Sapanca Lake, and the Izmit segment, it's right here. So you have the mean east-west velocity computed by InSAR data from 2002 and 2010. And so the red and green-blue pixels correspond to eastward and westward motion. So you can see the strike slip motion. And if we do some north-south profile,
we can observe an offset which is linked to the fault position. So we know that these segments are seismically creeping during this period. So now if you try to understand a little bit more the creep behavior along the Izmit segment, we can try to see what is happening again a few years later. So you have this paper from Aslan et al. In 2019. Again, you have here a mean east-west velocity computed by InSAR data. So here it's the opposite for the color, so eastward and westward. And if we look at the Izmit segment here, they computed the cumulative displacement along the fault from September 2014 to July 2017. So each dot corresponds to InSAR data, and what you can see is that you have a continuous creep until December 2016, when you have a transient acceleration, which is also correlated with a creep meter record on the western side of the Izmit segment. So here you have the displacement on the creep meter. So they detected a transient event in 2016. But what about this event? We know that there is something here, and it's not really clear on the InSAR data. Well, hopefully. Zorpacci et al. 1 year later used here campaign GNSS stations. So here you have the stations close to the fault, and they studied the east cumulative displacement from these stations. And you can see that you have also a continuous creep, and in September 2015, you have another transient acceleration correlated with the creep meter record. So they highlighted another transient event. So what we have here is that the Izmit segment seems to be affected by at least 2 transient events, and it leads to some questions. What is the creep behavior of the Izmit segment 20 years after the earthquake? Is it still as seismically creeping with transient events or not, or is it locked? What can be the spatial relationship between the seismic, so the 1999 earthquake, and the seismic slip distributions? And what does this imply for the earthquake cycle? So in order to try to answer this question, we decided to extend the analysis of the creep dynamic of the Izmit segment by using InSAR data. So here, again, you have the Izmit segment. We try to use 3 tracks, 3 InSAR time series of deformation, which have been automatically processed from Sentinel-1 images in the framework of FlatSim. So the 3 tracks are overlaying the Izmit segment, and we take advantages of the 6 days revisit time of the Sentinel-1 images since May 2016. So we have time series of deformation from May 2016 to the beginning of 2021. So now the idea is to try to extract the tectonic signal from this time series. To do so, we applied a post-processing specific sequence to our time series. And the first step was to decompose the signal into an horizontal and vertical time series of deformation. So by using an ascending and a descending track, we are able to do this decomposition. And because our segment is east-west, we can make the hypothesis that the north-south displacement is negligible rather than the east-west one. So like this, we obtain an east-west and a vertical time series of deformation overlaying our study area. Here you just have the mean velocity for each component. So you can see here the Izmit segment, the eastward and westward motion. And for the vertical velocity, the blue pixel corresponds to downward motion. So if we do some north-south profile across the fault, we obtain this kind of result. So here you have the fault position. You can see for the vertical profile in blue that there is, well, it seems that there is no link with the fault. However, for the east-west, we can see a sharp offset which is linked to the fault location, So we can make the hypothesis that we have a seismic creep along this segment. So to continue, we'll just use the east-west deformation. We make overcorrection just to remove the non-tectonic signals. And so now, what about the tectonic signal that we have? To see what is happening across the fault, we try to compute the fault-relative displacement. So the idea is to take pixels from the north side and pixels from the south side. By subtracting both time series, we can obtain the cumulative and relative displacement. So if we look at this free zone, we can obtain this kind of result. So again, from 2016 to 2021. And we have here the cumulative displacement across the fault. And here it's the creep meter records that we have. So as you can see clearly, we have 3 transient acceleration in December 2016, March 2018, and November 2019. The first and the last one are correlated with displacement recorded by the creep meters, and the first one is correlated with the previous paper that we saw. So we are able to detect 3 transient events, and between them, we have a steady state creep. But here, we are looking just the pixels really close to the fault. So if you try to go further, so we take boxes here, we can obtain these curves. Again, you can see the transient accelerations. However, we can see that for the first one, for example, it's less clear here in the data. So we are more sensitive. And between them, we have also a steady creep, but with a higher velocity than before. So this is interesting because what we can see is that if we look at close pixels or further pixels, we are able to detect 2 different mechanisms, the transient accelerations and the steady creep, but with different sensitivity. So it means that if we look at the slip inference, we should have some differences between the 2 mechanisms. So to continue, the idea is to separate both mechanisms. So we will estimate the displacement during the transient events, and we will, after remove this offset, and estimate the velocity during the period between them. And like this, we will study both mechanisms, but independently. So if we want to see the slip inference depth for both mechanisms, the idea is to use inversions. So we make the hypothesis of a 2 default interface below the Izmit segment in a layered elastic half space, using this velocity model. So the idea is to take into account here the presence of a sedimentary basin, which is all along the fault. Okay. And so we can try to do the inversions. So first, the transient slip. So we forgot about the 2016 event because it's too noisy for this exercise. And here you have the east-west displacement field for each event with north-south profile associated. Again, you can see the offset linked to the fault position. And after inversions, we can obtain this kind of slip distribution for both events. So what is interesting here is that the slip is localized within the sedimentary basin or just below it. So this is just for the transient acceleration. Now, if we look at what happened between these events, so we estimated the mean east-west velocity between the transient events, the north-south profile associated. You can see that we have still a sharp offset, so we can make the hypothesis of a superficial displacement. But you can also see that we have the far field motion, which is visible here. So the idea, if we want to optimize our inversion and have a precise result for the superficial displacement, we'll try to use an a priori model with the optimal locking depth to estimate this far field motion. But what is the locking depth for our study period? So to estimate the optimal locking depth, we try to use different a priori models. So the idea is to build, for example, an a priori model with a locking depth of 5, 11, or 16. We put to all the patches below the loading rate. Okay. After we run the inversions using a non-negative condition because we know that it's a pure strike slip motion. And after that, we can compute the root mean square errors between the model predictions and our data. What you can see here is the locking depth. We can see that if the locking depth is too shallow, we are not able at all to fit the data. If it's too deep, it seems okay. However, if we look at the slip distribution, you have these deep patches here with a velocity which is higher than the loading rate, so it seems unrealistic to have this kind of patches. So finally, we can estimate an optimal locking depth about 11 kilometers. And like this, we can obtain this kind of slip distribution. So you have the locking depth here, the locked zone just above, and you can see here that you have some patches which are really shallow and just below the sedimentary basin. So all together, we can see that we have two different mechanisms with two different patterns for our slip distribution. We have the transient slip, where the slip distribution is localized within the sedimentary basin, and the steady creep, where we have the laking depth, but we also have these patches which are really shallow. So if you try to compute the slip in depth for one cycle, when I said one cycle, it's one steady creep and one period of transient. We obtain this result. I'm sorry, it's small, but you can see here that in red you have the displacement due to the transient event. So it's between the surface and approximately 2 or 3 kilometer depth. And for the steady creep, we can see that the displacement, the main displacement, is deeper. It's between 2 and 5 kilometer depth. So it seems interesting to have close to the surface the displacement due to the transient slip, and just above the displacement due to the steady creep. So to conclude, if we put all of this together, all started with the 1999 earthquake below the Izmit segment. So here in green you have the seismic displacement computed by De et al. In 2002. You can observe just below the Izmit segment that there is a slip deficit. And if we look at 17 years later, we are able to estimate a locking depth of approximately 11 kilometers. And we are able to detect a shallow and steady creep between 2 and 5 kilometers. It seems to load the zone above, and so every 1.3 years we have a slow slip event which is just between the surface and 2 kilometer depth within the sedimentary basin. So what we can conclude about it is that it seems that the establishment of this steady creep and these transient events seem to compensate the slip deficit by releasing more strain. And because of the presence of the sedimentary basin, it seems that we have some difference in the frictional properties. And so we have two different mechanisms on this area. But we'll see with further detection if it's okay. So thanks a lot.
Really beautiful result. It's a little bit like the superstition hills fault, right? Where since 1987 you also have these increasingly sparse systematic creep events. So I can't help it, but looking at this, do you think eventually we could maybe see that the lock bubble shrinking with time?
With the two events that we have, I'm not sure. But yes, we should try if we are able to detect more events. For the moment, we just detected 4 events, so it's hard to see if the return period is really well estimated. But we try to see if we are able to detect further events with InSAR data or maybe GNSS stations to see. But it could be interesting.
Very impressive results. Thank you. How do you explain that you have steady creep that is faster than the previous?
So for this,
is it a resolution problem, or is it really something that?
Well, that's one possibility, because for the inversions we try to estimate the smooth parameters, optimal smooth parameters. So of course it will change the velocity, so it can be one explanation. After, why it can be higher?
It could be after sleep, but it's a long time afterwards, so would it be possible?
Yeah, we try to compare because there is a pair of GNSS stations here. So we try to see if we are still in the log decay. It seems that we should be still in the log decay. So maybe there is also a part of the after sleep area. Yeah, it's possible.
Any question from students or postdocs first? Okay, last question from your seat.
So are you planning to consider mechanical model following up on Roland's comment, you know, Matway and we've done, Romain discussed it, but if you add some heterogeneity, frictional heterogeneity in the sediment parts, and then you have like, you know, velocity strengthening zone just below it, one could probably model this kind of observations.
Sure. I think it could be a really nice. Yeah, and actually we don't have a lot of information about this sedimentary basin. We know the down deep limit, but there is no, well, in my knowledge, no tomography really precise on this point. But yeah, it could be very interesting to see because, yeah, we know that we don't have the perfect resolution, so maybe with this information it could help us. So yeah, thank you. Thank you. It's extending.
So, do you hear me well? Nice. So what I will be presenting today, it's kind of a side project after I submitted my thesis with some data that was left unpublished. And also because I wanted to experiment a bit with modeling and yeah. So I work in the Hellenic subduction system. I did a lot of tectonic geomorphology and I collected a lot of fault data in several of the islands. So in this side, also here in Eastern Crete, and then in this area over here. And most of the data was left unpublished, as I said. And the good thing about this data is that it's all of very recent activity because, yeah, I should say. The Hellenic subduction system is the fastest moving boundary in the Mediterranean region, and it has a high convergence rate of about 35 to 40 millimeters per year. And what you should remember throughout the presentation about this picture is that there is like 3 orders of features that are relevant for the discussion. The first order, it would be the plate interface. The second order would be these splay faults that are hundreds of kilometers long. I have plotted them as reverse, but there are scientists that have argued that they are normal or strike slip. It's an ongoing debate. And then it comes the third order features that are the upper crust normal faults that you can measure in the islands. And this is the data I have. So I know that the faults that I measured are recently active because of the concept of a post-glacial scarp. Post-glacial scarps are thought to be produced after the last glacial maximum. And we know that because every time that they have been dated, they end up being post-glacial. So I'm assuming that because all of the faults I measured look the same, like the ones that have been dated, then I assume that all of them have been active in the recent past. So they look like snakes in the field, and for the geophysicists out there, we measure the striations. Well, it doesn't look really nice, but it's like a rake, and you can have the fault data plotted as a moment tensor solution with a rake. And yeah, there are some issues, though, about the uncertainties of this. The first one being the Sadler effect, which is the increasing loss of information through time on all geological records, meaning that whatever geological record or data set you have, it will be always incomplete and you can do nothing about it. The second one is the potential of preservation that varies from island to island. So for example, here in Kythera, I measured 16 active faults, and because most of the rocks there are very competent and can preserve these scarps and activity, but here in Rhodos, which is twice or three times the size of Kythera, I measure only 7 faults because it's mainly soft sediments, and so the postglacial scarp is not preserved. And then it comes observational bias, which is related to accessibility. So for example, the Kera fault in Crete, over there in the corner, it takes 2 hours to walk to the scarp in thorny vegetation, and then you measure 3-4 striations, and you cannot move laterally to keep on measuring. Whereas sometimes you have smaller faults with small displacement, and they are along a road, so you just drive your car, stop every 100 meters and measure, and you have great control. So to avoid having faults with good access overrepresented in the stress inversion, what I did was to average all the measurements per fault into one plot. So instead of working with all the entries I had in the field, I worked with the process data set of 44 active faults, and then I took only like one value per fault. So I did the stress inversion with wind tensor, and what I wanted to do by inverting this data set is that in view of recent ruptures, earthquake ruptures, that have shown that the stress state of the crust changes through the seismic cycle, is that my assumption is that I should find this feature, these stress changes, in this data set and in this inversion. So instead of doing like a moment tensor sum of the faults, what I did was to take parameter f in the inversion. And the parameter f, what it does is that calculates the angle between the predicted slip under the stress that I calculated and compares it to my observation. So I make an inversion, and then in one particular fault that I accounted for in the inversion has an angle between predicted and observed slip that it's 50 degrees, it means that this fault did not rupture under the stress state that I calculated. If the F value is too high in general, then it means that the stress inversion I did yielded a stress state that probably never existed on the island. So because the data set is not that dense, I did this manually, and I ended up in the conclusion that actually variations in space and or time are required in all the islands to have all the faults that I measured to have ruptured in the recent past. And here's where I decided to start modeling, because here, all the faults are the same, are north-south. I had a very low F value, and I thought I could use the observed slip on the upper crust normal faults as a parameter to compare different types of kinematics on the Splay fault. So to run models of Coulomb stress changes of different rupture models for these faults in strike, slip, normal, reverse, whatever geometry, to see which one would give me as an output what I observed as kinematics in the upper crust faults. But, so I built my model. I made the source model for a magnitude 8 equivalent earthquake, and I placed my receiver faults in different parts of the rupture segment. But it was very fruitless because I was not having as input the initial state of stress of the crust. So I thought that then, knowing that there are studies that have shown that shear forces and gravitational forces are near balance and they kind of catch up to each other, I thought if I want to measure the effects on these faults of this coseismic Splay fault, then I would need to include gravitational forces as an initial state of stress of the crust to see the actual effects on these faults. But that also did not solve the issue because this force balance that is also kind of announced by critical wedge theory only works for the arc normal component of the convergence. And, oh no, well, yes. So in this plot, you have all the islands. It's many parameters because the discussion was very long, but what's important here is the green line that shows actually the obliquity. And the obliquity in this area, it's around 60 degrees. And I really don't know how to balance or how to include this strike-slip component of the convergence into the model to actually do what I wanted to do. But as a funny side note, I actually could do it in a much more simple way, meaning to differentiate which faults have been active interseismically on when or in which islands the stress variation were in space or time by simply comparing two moment tensor solutions. So the conclusion of the analysis without need of modeling so far was that actually in all islands, the stress changes are needed. In some of them, the stress changes are in space, and in some of them are in space and time, and others it's only in time. So, thank you.
Thank you very much. Any questions?
So you say it's postglacial scarp, right? And my first impression was it should be same timing, but then you show the different stress field. And my question will be, how about the time change, the biggest range?
What? Sorry?
Time. So I thought it should be same timing, and if it's same timing, maybe it's kind of similar stress field, right? You measured in your active faults, but in the conclusion you say, okay, you have rotation in space and time, so if you have some time range, will it be like, I don't know, 1,000 years, tens? What about the scale?
Postglacial means 16,000 years. And that, on the Hellenic case, it means up to 10 seismic cycles altogether. So I actually expected to find this variability in the stress. I did not expect it to be uniform. I just used typically like tools of structural geology that are normally used for like much denser data sets that change over million-year timescales, and a much smaller and reduced data set, but to explore stress variability within the seismic cycle. So
it's 1,000 years. The scale will be like
16 in the altogether.
No. I mean the change of the stress field. For example,
I don't know. To know that, I would need to do probably a seismic record in all of the faults, and that's not only very expensive, but like decades of effort.
Any other questions? Okay, so let's move on to the last. Oh, yes, thank you. Thank you. And let's move on to the last talk of the day with Anna Beatriz.
You got it right. Let me see. Can you help me put this thing in the back? I don't think I can reach it. You can try to do it right here.
It's a bit hard. Sorry.
Go ahead.
Okay, I will. Is it okay?
Yeah, I think so.
It will be much easier. It's very sorry.
It's harder to do.
Yeah. Okay, I can do it. I don't know if there is a way, but.
So how do you do it in advance?
Okay.
Cool. Okay. So, all right, I think I really do need my glasses for this. Okay, hello, can you hear me? Yes? thank you for having me. I'm very happy to be here and share with you some of the work that I've been doing. So I should start by saying that the title of this talk is more of an aspirational title. So this is where I want to get to. I'm not quite there yet, so I hope you're not very disappointed. But anyway, I hope you get excited about all the things that we can still learn from string partitioning and fault coupling in North and Central America. So let me start by talking to you about the tectonic setting of the region. I just learned from talking to some of you that we are not as famous as I thought. So maybe I should explain a little bit more about the tectonics in North and Central America. So what we have there is the interaction between three plates. So we have the North America plate over here, the Caribbean plate over here, and the Cocos plate over here. And this interaction is accommodated by several main features, not the only ones, but the most important. And so first we have the Polo-Chick-Motagua fault system, which is dealing with the North America-Caribbean motion. And this is, let's say, a pair of parallel faults. There are left lateral, one of which, the Motagua fault, was responsible for the 1976 earthquake that killed more than 23,000 people in 1976 and left like 1 million people homeless at a time where the population of the whole country was 5.5 million. So we are four times that right now, maybe, but at the time it was like a lot of people, thinking in percentages. Then, south of the Motagua fault, we have a series of north-south oriented extensional grabens that continue all the way to Honduras. Then we have our very own segment of the Middle America Trench, which is fairly active. And just for reference, we've had, in 2012, 3 earthquakes breaking several segments along Central America for the Middle America Trench that were of magnitudes larger than 7. And as if this wasn't enough, we also have like a series of faults that go along the volcanic arc. And so that's what's accommodating everything that's going on in Central America. So, okay, this I should have fixed. Let's see. There you go. So clearly, the seismic hazard of the region caught the interest of many people who do GNSS work. So that became an international effort to understand the area. And so there's been a lot of publications that have been built up on the work that's been done using GNSS. And so I got involved, I started getting involved like around here. Yeah, and so that's like the work that's been done. I just put it there for reference so that you can see that there was some very sustained interest along the years. And so in the golden era of GNSS work in Guatemala, we had, well, in the whole area, in fact, we had this network where you see the stars, which are continuous GNSS stations. The circles are campaign stations, and the colors tell you when they were installed. So they were not all there at the same time. It was like a network that was building up. And so using block modeling, well, before block modeling, they did time-dependent modeling. And so with the time-dependent modeling, they extracted this velocity field. This is a velocity field with respect to the Caribbean plate. And so that came from data from that beautiful network that no longer exists, as you see it there. But okay, so with this velocity field as an input, they work with a block model. Here more or less the blocks. I know it's not super clear to see, but this is not the subject of my talk. I just want to give it that as a reference. So the main results that came out of it were that for the North America-Caribbean boundary, so the Polo-Chick-Motagua fault system, we see that the velocities along the Motagua fault are decreasing from east to west. So that's like the main idea here, while the velocities in the Polo-Chick fault are much smaller and more or less constant, let's say. And the Motagua fault is accommodating about 80% of the deformation over there with respect to the, compared to what we get from the Polo-Chick fault. What else? That should be the most important thing for this part. And so now if we move to the Forearc sliver, which will be this block that we cut from the Caribbean plate because it's moving independently as we see, we also see a decrease in velocities with respect to the Caribbean fault as we move from east to west. And it also seems that this deformation is being transferred to the region of the grabens as we move to the west. So that's the other interesting thing that's going on there. Then if we think of the graben region, since this is GNSS, and so we don't have like the super dense network around the grabens, they took this big rectangle, they grabbed all the stations that were there, they obtained the east component of the velocity, and this is the plot that you get. And so what we see is that the extension of this part of the Caribbean plate is very focused in the area of the grabens. And so not only it is focused, but you see that the gradient is not just like from here to there, but it has like some sort of steps that makes us think that we should pay more attention at what's going on in the grabens instead of just thinking that there are other faults that are dangerous and not these ones. And about the subduction zone, what was found was, here you can see the locking along the subduction zone, and what they see is that we have some sort of weak locking when we are in El Salvador, and this becomes strong locking when we go to Mexico. And so with not much detail, but that's what we can see. So the idea was to see, okay, what can we see with InSAR that we couldn't see with GNSS? And so we wanted to answer a few questions that have been around for some time. And one of them is to see if there's creep happening in the Motagua fault, if there are coupling variations along the subduction zone, more detailed than what we can see with GPS, and which structures are accommodating the extension of the Caribbean waves. And for that, we used Sentinel-1 images. And we tried for some time to work with the NSBAS technique. We were unsuccessful as beating out the noise out of the signal. I have not given up yet, let me tell you. But in the meantime, since we needed to move forward, we asked our colleagues at DLR if they could give it a try. And after some interactions, they worked with a technique that uses persistent scatterers and distributed scatterers. And what we were able to get was this. So these are the velocity maps in the direction of line of sight. They are gorgeous, right? So we have these velocity maps for the ascending and descending tracks. And the little circles are the GNSS velocities projected onto line of sight. I need to clarify that for this projection of the velocities on GNSS, I'm just taking the horizontal components. I have plots somewhere else where you can see the ones that include the verticals, but I did this because the model that was derived from GPS only used the horizontal velocities. And I'm going to pull up the model, so it's just to be consistent with that. And also these velocities, when I projected them, were in the ITRF frame of reference. So I grabbed the model, the preferred model from GNSS, and I forward model what the InSAR should look like according to it. And so this is what the model says. And so we see that our InSAR velocity fields are in good agreement with the GNSS velocity data. If I put on the verticals, it's not as beautiful, but it's still very decent. And then that there's a good first order agreement with the GNSS-based data. But of course, there are differences. And other than the obvious differences that will come from the delimitation of the blocks in the model, which will never be perfect, there's also the variations change along the borders of the blocks. There's some sort of subsidence going on in Guatemala City, probably hydrological. There's some stuff going on here in Honduras. There are many things that we are happy to see because those are the extra things that we can learn using InSAR. So, okay. So here you see some profiles that go from 1 to 7, going from Western Guatemala to El Salvador. And then we have this one that cuts the graben, so just for reference. And so here are those profiles where the orange line is what the model says we should be getting. And then you get the data with some median to help us see something. So I'm not going to stop a long time on this, but we can definitely track the velocity gradients across the Motagua fault. But clearly, at some points, the Mottoa fault is not quite exactly what the model said it was. Like it's a little bit shifted, but this is to be expected, and this will help us also to improve the models. We can also track the smaller or almost no gradients across the Polochik fault, and again, the fault might be, in some cases, a little bit shifted where the model put it. But what I really like is that we see that the behavior from the volcanic arc faults and the Forearc sliver does not match the model, which we expected if the model didn't even take into account the verticals, which are important for the subduction zone, and also that the behavior changes as we move along the profiles. So there is something that was definitely not accounted by the GNSS model, and we see it also over here, that we should be taking into account. Also, there are other things like this little bump over here. I want to know what it is. No, it's this one. This is the one that I want to know what it is because it has the same sign on the two tracks, and I need to figure out what is the feature that's causing that and some other things. Now, for the one that crosses the grabens, here you see how the profile crosses the different block boundaries, and these are the lines that we get here. And we see that the model definitely is way too simple to account for the complexity that's happening here. So we see that here at least one more structure from the grabens should be taken into account, and maybe there are other things happening in other areas too. So, regarding some of the other questions, what's going on with the Mottoa fault? So we did like a ton of profiles that are 4 kilometers long to see what's going on along the Mottoa fault, and we find for several profiles on this yellow segment that they have this behavior that it's telling us that there's probably creep going on, which is something that we really, really wanted to know. And so these are preliminary results, but we see, like for the 3 red profiles, we have these results, while, for example, for this one, which is profile 10, I think, no, this is 10, and that's 42, we don't quite see the same behavior. So we really need to take a closer look at what's going on here, but this is very encouraging regarding the existence of creep in the Mottoa fault. This is just to see the values of creep that we measure, well, that we calculate, estimate with for the different tracks. And so if we want to compare this with something else, we have here a very famous figure of the co-seismic slip of the 76 earthquake. This is the figure from Plafker et al. It's very famous. And so what I put here is, am I there? No. What I have here is these stars are giving me those co-seismic slip values. There are some other stars from other measurements that may or may not have some after zip in them. And here are the values of the creep. So it kind of looks like when we get high magnitude creep, it kind of matches the regions where the co-seismic creep didn't reach the average slip for the earthquake. So maybe I am just seeing patterns where there are none, but it's worth still exploring and also try to match this with the after what was observed during this earthquake. Finally, for the subduction zone, we have all of these profiles that are normal to the trend. Of course, this is the coast, so there's a long part of the profiles where we see nothing. But the idea is that from what we see, well, first, they are very noisy because it's very hard to get good data near the coast. But we do see that there's a changing curvature as we move along the profiles which are color-coded. And so, although I know that it's not as simple as saying that this completely depends on the locking distribution and the subduction zone, because there is also the intervention of the volcanic arc faults on these profiles, we do think that a lot of what we're seeing here was impossible to resolve with the GNSS network that was active at the time. And so we are very, very hopeful that we will be able to get a better hold of what the locking distribution is in the subduction zone with this data. So this is a very, very, very short version of a super long to-do list with this information. And so hopefully we get beautiful results. Maybe the Mottoa fault will make it to the presentation showing gorgeous faults with with creep at some point. So I welcome any questions you may have and also suggestions on how to go forward or the things that we can do. So thank you.
Can you show again the profiles on the subduction zone part? Because I was wondering what was making you pointing toward the influence of coupling. Because when I look at the profiles on top, I see opposite senses of motion on the ascending and descending tracks, and so I was more expecting what you were referring to in the title, which is the partitioning.
Yeah. So I mean, in fact, that's what we need to kind of figure out how to separate if we see anything. I mean, and the idea is that, for example, for the bluish ones, we know that the faults here that go along the volcanic arc in El Salvador are, I'm going to say, more active and probably have more locking than the ones than when you go to Guatemala. And so that part of the locking, it's going to be showing some sort of arctangent thingy going on here on top of whatever it is that's coming from the subduction zone. So from the subduction, we will expect vertical deformation instead of the east-westish motion there. So we don't know exactly what we are seeing here. We don't know what's the contribution of each one of these motions. And that's what we want to try to resolve.
And is this fault that seems to go across the arc, is it mapped? Has it been?
Yes, I must have it somewhere. Let me see if it's. No, that doesn't go to El Salvador. So okay, I'm not showing the actual map, but this was based on the actual fault. So you have like a series of faults here. Then this step here, it's some bookshelf faulting that's going on here, so it gets messy around here. It's not clear what's happening. And then it continues here into Guatemala. So this one is very productive in terms of earthquakes. This one, not so much, and we are getting swarms around here like every now and then. And so since it's also a volcanic environment, it's like what's causing the earthquakes, what's going on here. But it's way less active, I'm going to say, I don't know if it's the proper word, than what we get in El Salvador, where you get more often sort of large earthquakes that keep people on their toes. So, yeah.
This is really beautiful data, given the environment. As you said yourself, right, you really want the vertical to be able to address this trade-off between internal fault deformation and subduction coupling related deformation. Now, you didn't get to show us the vertical, but you have seen.
We can check it out if you want to later on.
From what you've seen, do you think it will allow you to, better constrain what the coupling is, or do you find that vertical is strange? I'm not sure.
So
any model I can explain.
Hopefully, the InSAR will, but we haven't really tried that out to get a sense of how good it is, because it was very hard to get data all the way to the coast. And so it's, you can still be suspicious of whether did we eliminate too much or did we, in order to actually get there. So we still need to try some things to get a hold of that. But when they did the GPS modeling, where the verticals were evidently way more noisy than the horizontals, when I put them on top of this, they don't really show me a pattern. So I can see why they didn't use them anyway, because you don't really see clearly something that tells you this is what's going on. And it's probably because much of the hinged deal that happens in the subduction zones is happening before you reach the coast. So maybe we won't be able to see it, I don't know, because much of the behavior doesn't really change. I did many forward models of the subduction zone using the GPS model, but varying the locking distribution and everything. And in many cases, what you see when you reach the land, doesn't change that much, and the large changes happen in the portion that's still on sea. But I have not given up on that either, so there's still much to do. So yeah.
Okay, I think everyone is hungry, so we're stopping.
Yeah.
Please stay in the room if you want to. And thank you.
Thank you.